Hey everyone, Grant here. This is the first video in a series on the essence of calculus, and I'll be publishing the following videos once per day for the next 10 days. The goal here, as the name suggests, is to really get the heart of the subject out in one binge-watchable set. But with a topic that's as broad as calculus, there's a lot of things that can mean, so here's what I have in mind specifically. Calculus has a lot of rules and formulas which are often presented as things to be memorized. Lots of derivative formulas, the product rule, the chain rule, implicit differentiation, the fact that integrals and derivatives are opposite, Taylor series, just a lot of things like that. And my goal is for you to come away feeling like you could have invented calculus yourself. That is, cover all those core ideas, but in a way that makes clear where they actually come from and what they really mean using an all-around visual approach. Inventing math is no joke, and there is a difference between being told why something's true and actually generating it from scratch. But at all points, I want you to think to yourself, if you were an early mathematician, pondering these ideas and drawing out the right diagrams, does it feel reasonable that you could have stumbled across these truths yourself? In this initial video, I want to show how you might stumble into the core ideas of calculus by thinking very deeply about one specific bit of geometry, the area of a circle. Maybe you know that this is pi times its radius squared, but why? Is there a nice way to think about where this formula comes from? Well, contemplating this problem and leaving yourself open to exploring the interesting thoughts that come about can actually lead you to a glimpse of three big ideas in calculus: integrals, derivatives, and the fact that they're opposites. But the story starts more simply, just you and a circle, let's say with radius 3. You're trying to figure out its area, and after going through a lot of paper trying different ways to chop up and rearrange the pieces of that area, many of which might lead to their own interesting observations, maybe you try out the idea of slicing up the circle into many concentric rings. This should seem promising because it respects the symmetry of the circle, and math has a tendency to reward you when you respect its symmetries. Let's take one of those rings, which has some inner radius r that's between 0 and 3. If we can find a nice expression for the area of each ring like this one, and if we have a nice way to add them all up, it might lead us to an understanding of the full circle's area. Maybe you start by imagining straightening out this ring. And you could try thinking through exactly what this new shape is and what its area should be, but for simplicity, let's just approximate it as a rectangle. The width of that rectangle is the circumference of the original ring, which is 2 pi times r, right? I mean, that's essentially the definition of pi. And its thickness? Well, that depends on how finely you chopped up the circle in the first place, which was kind of arbitrary. In the spirit of using what will come to be standard calculus notation, let's call that thickness dr, for a tiny difference in the radius from one ring to the next. Maybe you think of it as something like 0.1. So, approximating this unwrapped ring as a thin rectangle, its area is 2 pi times r, the radius, times dr, the little thickness. And even though that's not perfect, for smaller and smaller choices of dr, this is actually going to be a better and better approximation for that area, since the top and the bottom sides of this shape are going to get closer and closer to being exactly the same length. So let's just move forward with this approximation, keeping in the back of our minds that it's slightly wrong, but it's going to become more accurate for smaller and smaller choices of dr. That is, if we slice up the circle into thinner and thinner rings. So just to sum up where we are, you've broken up the area of the circle into all of these rings, and you're approximating the area of each one of those as 2 pi times its radius times dr, where the specific value for that inner radius ranges from 0 for the smallest ring up to just under 3 for the biggest ring, spaced out by whatever the thickness is that you choose for dr, something like 0.1. And notice that the spacing between the values here corresponds to the thickness dr of each ring, the difference in radius from one ring to the next. In fact, a nice way to think about the rectangles approximating each ring's area is to fit them all upright side by side along this axis. Each one has a thickness dr, which is why they fit so snugly right there together, and the height of any one of these rectangles sitting above some specific value of r, like 0.6, is exactly 2 pi times that value. That's the circumference of the corresponding ring that this rectangle approximates. Pictured like this, 2 pi r can actually get kind of tall for the screen. I mean, 2 times pi times 3 is around 19, so let's just throw up a y-axis that's scaled a little differently so that we can actually fit all of these rectangles on the screen. A nice way to think about this setup is to draw the graph of 2 pi r, which is a straight line that has a slope 2 pi. Each of these rectangles extends up to the point where it just barely touches that graph. Again, we're being approximate here. Each of these rectangles only approximates the area of the corresponding ring from the circle. But remember, that approximation, 2 pi r times dr, gets less and less wrong as the size of dr gets smaller and smaller. And this has a very beautiful meaning when we're looking at the sum of the areas of all those rectangles. For smaller and smaller choices of dr, you might at first think that that turns the problem into a monstrously large sum. I mean, there's many, many rectangles to consider, and the decimal precision of each one of their areas is going to be an absolute nightmare. But notice, all of their areas in aggregate just looks like the area under a graph. And that portion under the graph is just a triangle with a base of 3 and a height that's 2 pi times 3. So its area, 1/2 base times height, works out to be exactly pi times 3 squared. Or if the radius of our original circle was some other value, capital R, that area comes out to be pi times r squared. And that's the formula for the area of a circle. It doesn't matter who you are or what you typically think of math, that right there is a beautiful argument. But if you want to think like a mathematician here, you don't just care about finding the answer. You care about developing general problem-solving tools and techniques. So take a moment to meditate on what exactly just happened and why it worked. Because the way that we transitioned from something approximate to something precise is actually pretty subtle, and it cuts deep to what calculus is all about. You had this problem that could be approximated with the sum of many small numbers, each of which looked like 2 pi r times dr for values of r ranging between 0 and 3. Remember, the small number dr here represents our choice for the thickness of each ring, for example 0.1. And there are two important things to note here. First of all, not only is dr a factor in the quantities we're adding up, 2 pi r times dr, it also gives the spacing between the different values of r. And secondly, the smaller our choice for dr, the better the approximation. Adding all of those numbers could be seen in a different, pretty clever way as adding the areas of many thin rectangles sitting underneath a graph, the graph of the function 2 pi r in this case. Then, and this is key, by considering smaller and smaller choices for dr, corresponding to better and better approximations of the original problem, the sum, thought of as the aggregate area of those rectangles, approaches the area under the graph. And because of that, you can conclude that the answer to the original question, in full unapproximated precision, is exactly the same as the area underneath this graph. A lot of other hard problems in math and science can be broken down and approximated as the sum of many small quantities. Things like figuring out how far a car has traveled based on its velocity at each point in time. In a case like that, you might range through many different points in time, and at each one multiply the velocity at that time times a tiny change in time, dt, which would give the corresponding little bit of distance traveled during that little time. I'll talk through the details of examples like this later in the series, but at a high level, many of these types of problems turn out to be equivalent to finding the area under some graph, in much the same way that our circle problem did. This happens whenever the quantities that you're adding up, the one whose sum approximates the original problem, can be thought of as the areas of many thin rectangles sitting side by side like this. If finer and finer approximations of the original problem correspond to thinner and thinner rings, then the original problem is going to be equivalent to finding the area under some graph. Again, this is an idea we'll see in more detail later in the series, so don't worry if it's not 100% clear right now. The point now is that you, as the mathematician having just solved a problem by reframing it as the area under a graph, might start thinking about how to find the areas under other graphs. I mean, we were lucky in the circle problem that the relevant area turned out to be a triangle, but imagine instead something like a parabola, the graph of x squared. What's the area underneath that curve, say between the values of x equals 0 and x equals 3? Well, it's hard to think about, right? And let me reframe that question in a slightly different way. We'll fix that left endpoint in place at 0 and let the right endpoint vary. Are you able to find a function, a of x, that gives you the area under this parabola between 0 and x? A function, a of x, like this, is called an integral of x squared. Calculus holds within it the tools to figure out what an integral like this is, but right now, it's just a mystery function to us. We know it gives the area under the graph of x squared between some fixed left point and some variable right point, but we don't know what it is. And again, the reason we care about this kind of question is not just for the sake of asking hard geometry questions. It's because many practical problems that can be approximated by adding up a large number of small things can be reframed as a question about an area under a certain graph. And I'll tell you right now that finding this area, this integral function, is genuinely hard. And whenever you come across a genuinely hard question in math, a good policy is to not try too hard to get at the answer directly, since usually you just end up banging your head against a wall. Instead, play around with the idea, with no particular goal in mind. Spend some time building up familiarity with the interplay between the function defining the graph, in this case x squared, and the function giving the area. In that playful spirit, if you're lucky, here's something that you might notice. When you slightly increase x by some tiny nudge, dx, look at the resulting change in area, represented with this sliver that I'm going to call dA, for a tiny difference in area. That sliver can be pretty well approximated with a rectangle, one whose height is x squared and whose width is dx. And the smaller the size of that nudge, dx, the more that sliver actually looks like a rectangle. Now this gives us an interesting way to think about how a of x is related to x squared. A change to the output of a, this little dA, is about equal to x squared, where x is whatever input you started at, times dx, the little nudge to the input that caused a to change. Or rearranged, dA divided by dx, the ratio of a tiny change in a to the tiny change in x that caused it, is approximately whatever x squared is at that point. And that's an approximation that should get better and better for smaller and smaller choices of dx. In other words, we don't know what a of x is. That remains a mystery. But we do know a property that this mystery function must have. When you look at two nearby points, for example 3 and 3.001, consider the change to the output of a between those 2 points, the difference between the mystery function evaluated at 3.001 and evaluated at 3. That change, divided by the difference in the input values, which in this case is 0.001, should be about equal to the value of x squared for the starting input, in this case 3 squared. And this relationship between tiny changes to the mystery function and the values of x squared itself is true at all inputs, not just 3. That doesn't immediately tell us how to find a of x, but it provides a very strong clue that we can work with. And there's nothing special about the graph x squared here. Any function, defined as the area under some graph, has this property, that dA divided by dx, a slight nudge to the output of a, divided by a slight nudge to the input that caused it, is about equal to the height of the graph at that point. Again, that's an approximation that gets better and better for smaller choices of dx. And here, we're stumbling into another big idea from calculus: derivatives. This ratio, dA divided by dx, is called the derivative of a. Or more technically, the derivative is whatever this ratio approaches as dx gets smaller and smaller. I'll dive much more deeply into the idea of a derivative in the next video, but loosely speaking, it's a measure of how sensitive a function is to small changes in its input. You'll see as the series goes on that there are many ways that you can visualize a derivative, depending on what function you're looking at and how you think about tiny nudges to its output. And we care about derivatives because they help us solve problems. And in our little exploration here, we already have a slight glimpse of one way that they're used. They are the key to solving integral questions, problems that require finding the area under a curve. Once you gain enough familiarity with computing derivatives, you'll be able to look at a situation like this one, where you don't know what a function is, but you do know that its derivative should be x squared, and from that, reverse engineer what the function must be. And this back and forth between integrals and derivatives, where the derivative of a function for the area under a graph gives you back the function defining the graph itself, is called the fundamental theorem of calculus. It ties together the two big ideas of integrals and derivatives, and it shows how, in some sense, each one is an inverse of the other. All of this is only a high-level view, just a peek at some of the core ideas that emerge in calculus. And what follows in this series are the details for derivatives and integrals and more. At all points, I want you to feel that you could have invented calculus yourself. That if you drew the right pictures and played with each idea in just the right way, these formulas and rules and constructs that are presented could have just as easily popped out naturally from your own explorations. The goal here is simple. Explain what a derivative is. The thing is, though, there's some subtlety to this topic, and a lot of potential for paradoxes if you're not careful. So kind of a secondary goal is that you have an appreciation for what those paradoxes are and how to avoid them. You see, it's common for people to say that the derivative measures an instantaneous rate of change. But when you think about it, that phrase is actually an oxymoron. Change is something that happens between separate points in time. And when you blind yourself to all but just a single instant, there's not really any room for change. You'll see what I mean more as we get into it, but when you appreciate that a phrase like instantaneous rate of change is actually nonsense, I think it makes you appreciate just how clever the fathers of calculus were in capturing the idea that that phrase is meant to evoke, but with a perfectly sensible piece of math, the derivative. As our central example, I want you to imagine a car that starts at some point A, speeds up, and then slows down to a stop at some point B 100 meters away. And let's say it all happens over the course of 10 seconds. That's the setup to have in mind as we lay out what the derivative is. We could graph this motion, letting the vertical axis represent the distance traveled and the horizontal axis represent time. So at each time t, represented with a point somewhere on this horizontal axis, the height of the graph tells us how far the car has traveled in total after that amount of time. It's pretty common to name a distance function like this s of t. I would use the letter d for distance, but that guy already has another full-time job in calculus. Initially, this curve is quite shallow, since the car is slow to start. During that first second, the distance that it travels doesn't really change that much. Then, for the next few seconds, as the car speeds up, the distance traveled in a given second gets larger, which corresponds to a steeper slope in this graph. And then towards the end, when it slows down, that curve shallows out again. And if we were to plot the car's velocity in meters per second as a function of time, it might look like this bump. At early times, the velocity is very small. Up to the middle of the journey, the car builds up to some maximum velocity, covering a relatively large distance each second. Then it slows back down towards a speed of 0. And these two curves here are definitely related to each other, right? If you change the specific distance versus time function, you're going to have some different velocity versus time function. And what we want to understand is the specifics of that relationship. Exactly how does velocity depend on a distance versus time function? And to do that, it's worth taking a moment to think critically about what exactly velocity means here. Intuitively, we all might know what velocity at a given moment means. It's just whatever the car's speedometer shows in that moment. And intuitively, it might make sense that the car's velocity should be higher at times when this distance function is steeper, when the car traverses more distance per unit time. But the funny thing is, velocity at a single moment makes no sense. If I show you a picture of a car, just a snapshot in an instant, and I ask you how fast it's going, you'd have no way of telling me. What you'd need are two separate points in time to compare. That way you can compute whatever the change in distance across those times is, divided by the change in time. Right? I mean, that's what velocity is. It's the distance traveled per unit time. So how is it that we're looking at a function for velocity that only takes in a single value of t, a single snapshot in time? It's weird, isn't it? We want to associate individual points in time with a velocity, but actually computing velocity requires comparing two separate points in times. If that feels strange and paradoxical, good! You're grappling with the same conflicts that the fathers of calculus did. And if you want a deep understanding for rates of change, not just for a moving car, but for all sorts of things in science, you're going to need to resolve this apparent paradox. First, I think it's best to talk about the real world, and then we'll go into a purely mathematical one. Let's think about what the car's speedometer is probably doing. At some point, say 3 seconds into the journey, the speedometer might measure how far the car goes in a very small amount of time, maybe the distance traveled between 3 seconds and 3.01 seconds. Then it could compute the speed in meters per second as that tiny distance traversed in meters divided by that tiny time, 0.01 seconds. That is, a physical car just sidesteps the paradox and doesn't actually compute speed at a single point in time. It computes speed during a very small amount of time. So let's call that difference in time dt, which you might think of in this case as 0.01 seconds, and let's call that resulting difference in distance ds. So the velocity at some point in time is ds divided by dt, the tiny change in distance over the tiny change in time. Graphically, you can imagine zooming in on some point of this distance versus time graph above t equals 3. That dt is a small step to the right, since time is on the horizontal axis. And that ds is the resulting change in the height of the graph, since the vertical axis represents the distance traveled. So ds divided by dt is something you can think of as the rise over run slope between two very close points on this graph. Of course, there's nothing special about the value t equals 3. We could apply this to any other point in time, so we consider this expression ds over dt to be a function of t, something where I can give you a time t and you can give me back the value of this ratio at that time, the velocity as a function of time. So, for example, when I had the computer draw this bump curve here, the one representing the velocity function, here's what I had the computer actually do. First, I chose a small value for dt. I think in this case it was 0.01. Then I had the computer look at a whole bunch of times t between 0 and 10 and compute the distance function s at t plus dt, and then subtract off the value of that function at t. In other words, that's the difference in the distance traveled between the given time t and the time 0.01 seconds after that. Then you can just divide that difference by the change in time, dt, and that gives you velocity in meters per second around each point in time. So with a formula like this, you could give the computer any curve representing any distance function s of t, and it could figure out the curve representing velocity. So now would be a good time to pause, reflect, make sure that this idea of relating distance to velocity by looking at tiny changes makes sense. Because what we're going to do is tackle the paradox of the derivative head on. This idea of ds over dt, a tiny change in the value of the function s, divided by the tiny change in the input that caused it, that's almost what a derivative is. And even though a car's speedometer will actually look at a concrete change in time, like 0.01 seconds, and even though the drawing program here is looking at an actual concrete change in time, in pure math, the derivative is not this ratio ds dt for a specific choice of dt. Instead, it's whatever that ratio approaches as your choice for dt approaches 0. Luckily, there is a really nice visual understanding for what it means to ask what this ratio approaches. Remember, for any specific choice of dt, this ratio ds dt is the slope of a line passing through two separate points on the graph, right? Well, as dt approaches 0, and as those 2 points approach each other, the slope of the line approaches the slope of a line that's tangent to the graph at whatever point t we're looking at. So the true, honest-to-goodness, pure math derivative is not the rise over run slope between two nearby points on the graph. It's equal to the slope of a line tangent to the graph at a single point. Now, notice what I'm not saying. I am not saying that the derivative is whatever happens when dt is infinitely small, whatever that would mean. Nor am I saying that you plug in 0 for dt. This dt is always a finitely small, non-zero value. It's just that it approaches 0 is all. I think that's really clever. Even though change in an instant makes no sense, this idea of letting dt approach zero is a really sneaky backdoor way to talk reasonably about the rate of change at a single point in time. Isn't that neat? It's kind of flirting with the paradox of change in an instant without ever needing to actually touch it. And it comes with such a nice visual intuition too, as the slope of a tangent line to a single point on the graph. And because change in an instant still makes no sense, I think it's healthiest for you to think of this slope not as some instantaneous rate of change, but instead as the best constant approximation for a rate of change around a point. By the way, it's worth saying a couple words on notation here. Throughout this video, I've been using dt to refer to a tiny change in t, with some actual size, and ds to refer to the resulting change in s, which again has an actual size. And this is because that's how I want you to think about them. But the convention in calculus is that whenever you're using the letter d like this, you're kind of announcing your intention that eventually you're going to see what happens as dt approaches zero. For example, the honest-to-goodness pure math derivative is written as ds divided by dt, even though it's technically not a fraction per se, but whatever that fraction approaches for smaller and smaller nudges in t. I think a specific example should help here. You might think that asking about what this ratio approaches for smaller and smaller values would make it much more difficult to compute. But weirdly, it kind of makes things easier. Let's say that you have a given distance versus time function that happens to be exactly t cubed. So after 1 second, the car has traveled 1 cubed equals 1 meters. After 2 seconds, it's traveled 2 cubed, or 8 meters, and so on. Now what I'm about to do might seem somewhat complicated, but once the dust settles, it really is simpler. And more importantly, it's the kind of thing that you only ever have to do once in calculus. Let's say you wanted to compute the velocity, ds divided by dt, at some specific time, like t equals 2. And for right now, let's think of dt as having an actual size, some concrete nudge. We'll let it go to 0 in just a bit. The tiny change in distance between 2 seconds and 2 plus dt seconds, well, that's s of 2 plus dt minus s of 2. And we divide that by dt. Since our function is t cubed, that numerator looks like 2 plus dt cubed minus 2 cubed. And this is something we can work out algebraically. Again, bear with me. There's a reason that I'm showing you the details here. When you expand that top, what you get is 2 cubed plus 3 times 2 squared dt plus 3 times 2 times dt squared plus dt cubed, and all of that is minus 2 cubed. Now there's a lot of terms, and I want you to remember that it looks like a mess, but it does simplify. Those 2 cubed terms, they cancel out. And then everything remaining here has a dt in it. And since there's a dt on the bottom there, many of those cancel out as well. What this means is that the ratio ds divided by dt has boiled down into 3 times 2 squared plus, well, 2 different terms that each have a dt in them. So if we ask what happens as dt approaches 0, representing the idea of looking at a smaller and smaller change in time, we can just completely ignore those other terms. By eliminating the need to think about a specific dt, we've actually eliminated a lot of the complication in the full expression. So what we're left with is this nice clean 3 times 2 squared. You can think of that as meaning that the slope of a line tangent to the point at t equals 2 of this graph is exactly 3 times 2 squared, or 12. And of course, there's nothing special about the time t equals 2. We could more generally say that the derivative of t cubed as a function of t is 3 times t squared. Now take a step back, because that's beautiful. The derivative is this crazy complicated idea. We've got tiny changes in distance over tiny changes in time, but instead of looking at any specific one of those, we're talking about what that thing approaches. I mean, that's a lot to think about. And yet what we've come out with is such a simple expression, 3 times t squared. And in practice, you wouldn't go through all this algebra each time. Knowing that the derivative of t cubed is 3t squared is one of those things that all calculus students learn how to do immediately without having to rederive it each time. And in the next video, I'm going to show you a nice way to think about this and a couple other derivative formulas in really nice geometric ways. But the point I want to make by showing you all of the algebraic guts here is that when you consider the tiny change in distance caused by a tiny change in time for some specific value of dt, you'd have kind of a mess. But when you consider what that ratio approaches as dt approaches 0, it lets you ignore much of that mess, and it really does simplify the problem. That right there is kind of the heart of why calculus becomes useful. Another reason to show you a concrete derivative like this is that it sets the stage for an example of the kind of paradoxes that come about if you believe too much in the illusion of instantaneous rate of change. So think about the actual car traveling according to this t-cubed distance function, and consider its motion at the moment t equals 0, right at the start. Now ask yourself whether or not the car is moving at that time. On the one hand, we can compute its speed at that point using the derivative, 3t squared, which for time t equals 0 works out to be 0. Visually, this means that the tangent line to the graph at that point is perfectly flat, so the car's quote-unquote instantaneous velocity is 0. And that suggests that obviously it's not moving. But on the other hand, if it doesn't start moving at time 0, when does it start moving? Really, pause and ponder that for a moment. Is the car moving at time t equals 0? Do you see the paradox? The issue is that the question makes no sense. It references the idea of change in a moment, but that doesn't actually exist. That's just not what the derivative measures. What it means for the derivative of a distance function to be 0 is that the best constant approximation for the car's velocity around that point is 0 meters per second. For example, if you look at an actual change in time, say between time 0 and 0.1 seconds, the car does move. It moves 0.001 meters. That's very small, and importantly, it's very small compared to the change in time, giving an average speed of only 0.01 meters per second. And remember, what it means for the derivative of this motion to be 0 is that for smaller and smaller nudges in time, this ratio of meters per second approaches 0. But that's not to say that the car is static. Approximating its movement with a constant velocity of 0 is, after all, just an approximation. So whenever you hear people refer to the derivative as an instantaneous rate of change, a phrase which is intrinsically oxymoronic, I want you to think of that as a conceptual shorthand for the best constant approximation for rate of change. In the next couple of videos, I'll be talking more about the derivative, what it looks like in different contexts, how do you actually compute it, why is it useful, things like that, focusing on visual intuition as always. Now that we've seen what a derivative means and what it has to do with rates of change, our next step is to learn how to actually compute these guys. As in, if I give you some kind of function with an explicit formula, you'd want to be able to find what the formula for its derivative is. Maybe it's obvious, but I think it's worth stating explicitly why this is an important thing to be able to do. Why much of a calculus student's time ends up going towards grappling with derivatives of abstract functions rather than thinking about concrete rate of change problems. It's because a lot of real-world phenomena, the sort of things that we want to use calculus to analyze, are modeled using polynomials, trigonometric functions, exponentials, and other pure functions like that. So if you build up some fluency with the ideas of rates of change for those kinds of pure abstract functions, it gives you a language to more readily talk about the rates at which things change in concrete situations that you might be using calculus to model. But it is way too easy for this process to feel like just memorizing a list of rules. And if that happens, if you get that feeling, it's also easy to lose sight of the fact that derivatives are fundamentally about just looking at tiny changes to some quantity and how that relates to a resulting tiny change in another quantity. So in this video and in the next one, my aim is to show you how you can think about a few of these rules intuitively and geometrically. And I really want to encourage you to never forget that tiny nudges are at the heart of derivatives. Let's start with a simple function, like f of x equals x squared. What if I asked you its derivative? That is, if you were to look at some value x, like x equals 2, and compare it to a value slightly bigger, just dx bigger, what's the corresponding change in the value of the function, df? And in particular, what's df divided by dx, the rate at which this function is changing per unit change in x? As a first step for intuition, we know that you can think of this ratio df dx as the slope of a tangent line to the graph of x squared. And from that, you can see that the slope generally increases as x increases. At 0, the tangent line is flat, and the slope is 0. At x equals 1, it's something a bit steeper. At x equals 2, it's steeper still. But looking at graphs isn't generally the best way to understand the precise formula for a derivative. For that, it's best to take a more literal look at what x squared actually means. And in this case, let's go ahead and picture a square whose side length is x. If you increase x by some tiny nudge, some little dx, what's the resulting change in the area of that square? That slight change in area is what df means in this context. It's the tiny increase to the value of f of x equals x squared caused by increasing x by that tiny nudge dx. Now you can see that there's 3 new bits of area in this diagram, 2 thin rectangles and a minuscule square. The 2 thin rectangles each have side lengths of x and dx, so they account for 2 times x times dx units of new area. For example, let's say x was 3 and dx was 0.01, then that new area from these 2 thin rectangles would be 2 times 3 times 0.01, which is 0.06, about 6 times the size of dx. That little square there has an area of dx squared, but you should think of that as being really tiny, negligibly tiny. For example, if dx was 0.01, that would be only 0.0001. And keep in mind, I'm drawing dx with a fair bit of width here just so we can actually see it, but always remember, in principle, dx should be thought of as a truly tiny amount. And for those truly tiny amounts, a good rule of thumb is that you can ignore anything that includes a dx raised to a power greater than 1. That is, a tiny change squared is a negligible change. What this leaves us with is that df is just some multiple of dx. And that multiple, 2x, which you could also write as df divided by dx, is the derivative of x squared. For example, if you were starting at x equals 3, then as you slightly increase x, the rate of change in the area per unit change in length added, dx squared over dx, would be 2 times 3, or 6. And if instead you were starting at x equals 5, then the rate of change would be 10 units of area per unit change in x. Let's go ahead and try a different simple function, f of x equals x cubed. This is going to be the geometric view of the stuff that I went through algebraically in the last video. What's nice here is that we can think of x cubed as the volume of an actual cube, whose side lengths are x. And when you increase x by a tiny nudge, a tiny dx, the resulting increase in volume is what I have here in yellow. That represents all the volume in a cube with side lengths x plus dx that's not already in the original cube, the one with side length x. It's nice to think of this new volume as broken up into multiple components, but almost all of it comes from these 3 square faces. Or, said a little more precisely, as dx approaches 0, those 3 squares comprise a portion closer and closer to 100% of that new yellow volume. Each of those thin squares has a volume of x squared times dx, the area of the face times that little thickness dx. So in total, this gives us 3x squared dx of volume change. And to be sure, there are other slivers of volume here along the edges and that tiny one in the corner, but all of that volume is going to be proportional to dx squared, or dx cubed, so we can safely ignore them. Again, this is ultimately because they're going to be divided by dx. And if there's still any dx remaining, then those terms aren't going to survive the process of letting dx approach 0. What this means is that the derivative of x cubed, the rate at which x cubed changes per unit change of x, is 3 times x squared. What that means in terms of graphical intuition is that the slope of the graph of x cubed at every single point x is exactly 3x squared. And reasoning about that slope, it should make sense that this derivative is high on the left, and then 0 at the origin, and then high again as you move to the right. But just thinking in terms of the graph would never have landed us on the precise quantity 3x squared. For that, we had to take a much more direct look at what x cubed actually means. Now, in practice, you wouldn't necessarily think of the square every time you're taking the derivative of x squared, nor would you necessarily think of this cube whenever you're taking the derivative of x cubed. Both of them fall under a pretty recognizable pattern for polynomial terms. The derivative of x to the 4th turns out to be 4x cubed. the derivative of x to the fifth is 5x to the fourth, and so on. Abstractly, you'd write this as the derivative of x to the n for any power n is n times x to the n minus 1. This right here is what's known in the business as the power rule. In practice, we all quickly just get jaded and think about this symbolically, as the exponent hopping down in front, leaving behind one less than itself, rarely pausing to think about the geometric delights that underlie these derivatives. That's the kind of thing that happens when these tend to fall in the middle of much longer computations. But rather than chalking it all off to symbolic patterns, let's just take a moment and think about why this works for powers beyond just 2 and 3. When you nudge that input x, increasing it slightly to x plus dx, working out the exact value of that nudged output would involve multiplying together these n separate x plus dx terms. The full expansion would be really complicated, but part of the point of derivatives is that most of that complication can be ignored. The first term in your expansion is x to the n. This is analogous to the area of the original square, or the volume of the original cube from our previous examples. For the next terms in the expansion, you can choose mostly x's with a single dx. Since there are n different parentheticals from which you could have chosen that single dx, this gives us n separate terms, all of which include n minus 1 x's times a dx, giving a value of x to the power n minus 1 times dx. This is analogous to how the majority of the new area in the square came from those 2 bars, each with area x times dx, or how the bulk of the new volume in the cube came from those 3 thin squares, each of which had a volume of x squared times dx. There will be many other terms in this expansion, but all of them are just going to be some multiple of dx squared, so we can safely ignore them. And what that means is that all but a negligible portion of the increase in the output comes from n copies of this x to the n minus 1 times dx. That's what it means for the derivative of x to the n to be n times x to the n minus 1. And even though, like I said, in practice you'll find yourself performing this derivative quickly and symbolically, imagining the exponent hopping down to the front, every now and then it's nice to just step back and remember why these rules work. Not just because it's pretty, and not just because it helps remind us that math actually makes sense and isn't just a pile of formulas to memorize, but because it flexes that very important muscle of thinking about derivatives in terms of tiny nudges. As another example, think of the function f of x equals 1 divided by x. Now, on the one hand, you could just blindly try applying the power rule, since 1 divided by x is the same as writing x to the negative 1. That would involve letting the negative 1 hop down in front, leaving behind one less than itself, which is negative 2. But let's have some fun, and see if we can reason about this geometrically, rather than just plugging it through some formula. The value 1 over x is asking, what number multiplied by x equals 1? So here's how I'd like to visualize it. Imagine a little rectangular puddle of water sitting in 2 dimensions, whose area is 1. And let's say that its width is x, which means that the height has to be 1 over x, since the total area of it is 1. So if x was stretched out to 2, then that height is forced down to 1/2. And if you increased x up to 3, then the other side has to be squished down to 1/3. This is a nice way to think about the graph of 1 over x, by the way. If you think of this width x of the puddle as being in the xy plane, then that corresponding output, 1 divided by x, the height of the graph above that point, is whatever the height of your puddle has to be to maintain an area of 1. So with this visual in mind, for the derivative, imagine nudging up that value of x by some tiny amount, some tiny dx. How must the height of this rectangle change so that the area of the puddle remains constant at 1? That is, increasing the width by dx adds some new area to the right here. So the puddle has to decrease in height by some d1 over x, so that the area lost off of that top cancels out the area gained. You should think of that d1 over x as being a negative amount, by the way, since it's decreasing the height of the rectangle. And you know what? I'm going to leave the last few steps here for you to pause and ponder and work out an ultimate expression. And once you reason out what d of 1 over x divided by dx should be, I want you to compare it to what you would have gotten if you had just blindly applied the power rule, purely symbolically, to x to the negative 1. And while I'm encouraging you to pause and ponder, here's another fun challenge if you're feeling up to it. See if you can reason through what the derivative of the square root of x should be. To finish things off, I want to tackle one more type of function, trigonometric functions. And in particular, let's focus on the sine function. So for this section, I'm going to assume that you're already familiar with how to think about trig functions using the unit circle, the circle with a radius 1 centered at the origin. For a given value of theta, like say 0.8, you imagine yourself walking around the circle starting from the rightmost point until you've traversed that distance of 0.8 in arc length. This is the same thing as saying that the angle right here is exactly theta radians, since the circle has a radius of 1. Then what sine of theta means is the height of that point above the x-axis. And as your theta value increases, and you walk around this circle, your height bobs up and down between negative 1 and 1. So when you graph sine of theta versus theta, you get this wave pattern, the quintessential wave pattern. And just from looking at this graph, we can start to get a feel for the shape of the derivative of the sine. The slope at 0 is something positive, since sine of theta is increasing there. And as we move to the right and sine of theta approaches its peak, that slope goes down to 0. Then the slope is negative for a little while the sine is decreasing, before coming back up to 0 as the sine graph levels out. And as you continue thinking this through and drawing it out, if you're familiar with the graph of trig functions, you might guess that this derivative graph should be exactly cosine of theta, since all the peaks and valleys line up perfectly with where the peaks and valleys for the cosine function should be. And spoiler alert, the derivative is in fact the cosine of theta. But aren't you a little curious about why it's precisely cosine of theta? I mean, you could have all sorts of functions with peaks and valleys at the same points that have roughly the same shape, but who knows, maybe the derivative of sine could have turned out to be some entirely new type of function that just happens to have a similar shape. Well, just like the previous examples, a more exact understanding of the derivative requires looking at what the function actually represents, rather than looking at the graph of the function. So think back to that walk around the unit circle, having traversed an arc with length theta and thinking about sine of theta as the height of that point. Now zoom into that point on the circle and consider a slight nudge of d theta along their circumference, a tiny step in your walk around the unit circle. How much does that tiny step change the sine of theta? How much does this increased d theta of arc length increase the height above the x-axis? Well, zoomed in close enough, the circle basically looks like a straight line in this neighborhood. So let's go ahead and think of this right triangle, where the hypotenuse of that right triangle represents the nudge d theta along their circumference, and that left side here represents the change in height, the resulting d sine of theta. Now this tiny triangle is actually similar to this larger triangle here, with the defining angle theta, and whose hypotenuse is the radius of the circle with length 1. Specifically, this little angle right here is precisely equal to theta radians. Now, think about what the derivative of sine is supposed to mean. It's the ratio between that d sine of theta, the tiny change to the height, divided by d theta, the tiny change to the input of the function. And from the picture, we can see that that's the ratio between the length of the side adjacent to the angle theta divided by the hypotenuse. Well, let's see. Adjacent divided by hypotenuse? That's exactly what the cosine of theta means. That's the definition of the cosine. So this gives us two different really nice ways of thinking about how the derivative of sine is cosine. One of them is looking at the graph and getting a loose feel for the shape of things based on thinking about the slope of the sine graph at every single point. And the other is a more precise line of reasoning, looking at the unit circle itself. For those of you that like to pause and ponder, see if you can try a similar line of reasoning to find what the derivative of the cosine of theta should be. In the next video, I'll talk about how you can take derivatives of functions who combine simple functions like these ones, either as sums or products or function compositions, things like that. And similar to this video, the goal is going to be to understand each one geometrically in a way that makes it intuitively reasonable and somewhat more memorable. In the last videos, I talked about the derivatives of simple functions, and the goal was to have a clear picture or intuition to hold in your mind that actually explains where these formulas come from. But of course, most of the functions you deal with in modeling the world involve somehow mixing or combining or tweaking these simple functions in some other way. So our natural next step is to understand how you take derivatives of more complicated combinations. And again, I don't want these to be something to memorize. I want you to have a clear picture in mind for where each one comes from. Now, this really boils down into three basic ways to combine functions. You can add them together, you can multiply them, and you can throw one inside the other, known as composing them. Sure, you could say subtracting them, but really that's just multiplying the second by -1 and adding them together. And likewise, dividing functions doesn't really add anything, because that's the same as plugging one inside the function 1 over x, and then multiplying the two together. So really, most functions you come across just involve layering together these three different types of combinations, though there's not really a bound on how monstrous things can become. But as long as you know how derivatives play with just those three combination types, you'll always be able to just take it step by step and peel through the layers for any kind of monstrous expression. So the question is, if you know the derivative of two functions, what is the derivative of their sum, of their product, and of the function composition between them? The sum rule is easiest, if somewhat tongue-twisting to say out loud. The derivative of a sum of two functions is the sum of their derivatives. But it's worth warming up with this example by really thinking through what it means to take a derivative of a sum of two functions, since the derivative patterns for products and for function composition won't be so straightforward, and they're going to require this kind of deeper thinking. For example, let's think about this function f of x equals sine of x plus x squared. It's a function where, for every input, you add together the values of sine of x and x squared at that point. For example, let's say at x equals 0.5, the height of the sine graph is given by this vertical bar, and the height of the x squared parabola is given by this slightly smaller vertical bar. And their sum is the length you get by just stacking them together. Now, for the derivative, you want to ask what happens as you nudge that input slightly, maybe increasing it up to 0.5 plus dx. The difference in the value of f between those two places is what we call df. And when you picture it like this, I think you'll agree that the total change in the height is whatever the change to the sine graph is, what we might call d sine of x, plus whatever the change to x squared is, dx squared. Now, we know that the derivative of sine is cosine, and remember what that means. It means that this little change, d sine of x, is about cosine of x times dx. It's proportional to the size of our initial nudge, dx, and the proportionality constant equals cosine of whatever input we happen to start at. Likewise, because the derivative of x squared is 2x, the change in the height of the x squared graph is going to be about 2 times x times whatever dx was. So, rearranging, df divided by dx, the ratio of the tiny change to this sum function to the tiny change in x that caused it, is indeed cosine of x plus 2x, the sum of the derivatives of its parts. But like I said, things are a bit different for products, and let's think through why. And let's think through why in terms of tiny nudges again. In this case, I don't think graphs are our best bet for visualizing things. Pretty commonly in math, at a lot of levels of math really, if you're dealing with a product of two things, it helps to understand it as some kind of area. In this case, maybe you try to configure some mental setup of a box where the side lengths are sine of x and x squared. But what would that mean? Well, since these are functions, you might think of those sides as adjustable, dependent on the value of x, which maybe you think of as this number that you can just freely adjust up and down. So getting a feel for what this means, focus on that top side there, who changes as the function sine of x. As you change this value of x up from 0, it increases up to a length of 1 as sine of x moves up towards its peak. And after that, it starts to decrease as sine of x comes down from 1. And in the same way, that height there is always changing as x squared. So f of x, defined as the product of these two functions, is going to be the area of this box. And for the derivative, let's think about how a tiny change to x by dx influences that area. What is that resulting change in area df? Well, the nudge dx caused that width to change by some small d sine of x, and it caused that height to change by some dx squared. And this gives us three little snippets of new area. A thin rectangle on the bottom, whose area is its width, sine of x, times its thin height, dx squared. And there's this thin rectangle on the right, whose area is its height, x squared, times its thin little width, d sine of x. And there's also this little bit in the corner, but we can ignore that. Its area is ultimately going to be proportional to dx squared, and as we've seen before, that becomes negligible as dx goes to 0. I mean, this whole setup is very similar to what I showed last video with the x squared diagram. And just like then, keep in mind that I'm using somewhat beefy changes here to draw things, just so that we can actually see them. But in principle, dx is something very, very small, and that means that dx squared and d sine of x are also very, very small. So, applying what we know about the derivative of sine and of x squared, that tiny change, dx squared, is going to be about 2x times dx. And that tiny change d sine of x, well, that's going to be about cosine of x times dx. As usual, we divide out by that dx to see that the ratio we want, df divided by dx, is sine of x times the derivative of x squared, plus x squared times the derivative of sine. And nothing we've done here is specific to sine or to x squared. This same line of reasoning would work for any two functions, g and h. And sometimes people like to remember this pattern with a certain mnemonic that you kind of sing in your head. Lefty right, righty left. In this example, where we have sine of x times x squared, lefty right means you take that left function, sine of x, times the derivative of the right, in this case 2x. Then you add on righty left. That right function, x squared, times the derivative of the left one, cosine of x. Now, out of context, presented as a rule to remember, I think this would feel pretty strange, don't you? But when you actually think of this adjustable box, you can see what each of those terms represents. Lefty right is the area of that little bottom rectangle. And righty left is the area of that rectangle on the side. By the way, I should mention that if you multiply by a constant, say 2 times sine of x, things end up a lot simpler. The derivative is just the same as the constant multiplied by the derivative of the function, in this case 2 times cosine of x. I'll leave it to you to pause and ponder and just kind of verify that that makes sense. Aside from addition and multiplication, the other common way to combine functions, and believe me, this one comes up all the time, is to shove one inside the other, function composition. For example, maybe we take the function x squared and we just shove it on inside sine of x to get this new function sine of x squared. What do you think the derivative of that new function is? To think this one through, I'm going to choose yet another way to visualize things, just to emphasize that in creative math, we've got lots of options. I'll put up 3 different number lines. The top one is going to hold the value of x, the second one is going to hold the value of x squared, and that third line is going to hold the value of sine of x squared. That is, the function x squared gets you from line 1 to line 2, and the function sine gets you from line 2 to line 3. As I shift around this value of x, maybe moving it up to the value 3, that second value stays pegged to whatever x squared is, in this case moving up to 9. And that bottom value, being sine of x squared, is going to go to whatever sine of 9 happens to be. So for the derivative, let's again start by just nudging that x value by some little dx. And I always think that it's helpful to think of x as starting at some actual concrete number, maybe 1.5 in this case. The resulting nudge to that second value, the change in x squared caused by such a dx, is dx squared. And we could expand this like we have before as 2x times dx, which for our specific input would be 2 times 1.5 times dx, but it actually helps to keep things written as dx squared, at least for now. And in fact, I'm going to go one step further. I'm going to give a new name to this x squared, maybe h, so that instead of writing dx squared for this nudge, we write dh. And this makes it easier to think about that third value, which is now pegged at sine of h. Its change is d sine of h, the tiny change caused by the nudge dh. And by the way, the fact that it's moving to the left while the dh bump is going to the right, that just means that this change, d sine of h, is going to be some kind of negative number. And once again, we can use our knowledge of the derivative of the sine. This d sine of h is going to be about cosine of h times dh. That's what it means for the derivative of sine to be cosine. And unfolding things, we can just replace that h with x squared again, so we know that that bottom nudge is going to have a size of cosine of x squared times dx squared. And in fact, let's unfold things even further. That intermediate nudge dx squared is going to be about 2x times dx. And it's always a good habit to remind yourself of what an expression like this actually means. In this case, where we started at x equals 1.5 up top, this whole expression is telling us that the size of the nudge on that third line is going to be about cosine of 1.5 squared times 2 times 1.5 times whatever the size of dx was. It's proportional to the size of dx, and this derivative is giving us that proportionality constant. Notice what we came out with here. We have the derivative of the outside function, and it's still taking in the unaltered inside function, and then we're multiplying it by the derivative of that inside function. Again, there is nothing special about sine of x or x squared. If you have any two functions, g of x and h of x, the derivative of their composition, g of h of x, is going to be the derivative of g evaluated on h, multiplied by the derivative of h. This pattern right here is what we usually call the chain rule. Notice, for the derivative of g, I'm writing it as dg dh instead of dg dx. On the symbolic level, this is a reminder that the thing you plug into that derivative is still going to be that intermediary function h. But more than that, it's an important reflection of what this derivative of the outer function actually represents. Remember, in our three-line setup, when we took the derivative of the sine on that bottom, we expanded the size of that nudge, d sine, as cosine of h times dh. This was because we didn't immediately know how the size of that bottom nudge depended on x. That's kind of the whole thing we were trying to figure out. But we could take the derivative with respect to that intermediate variable, h. That is, figure out how to express the size of that nudge on the third line as some multiple of dh, the size of the nudge on the second line. And it was only after that that we unfolded further by figuring out what dh was. So in this chain rule expression, we're saying, look at the ratio between a tiny change in g, the final output, to a tiny change in h that caused it, h being the value that we plug into g. Then multiply that by the tiny change in h divided by the tiny change in x that caused it. So notice, those dh's cancel out, and they give us a ratio between the change in that final output and the change to the input that, through a certain chain of events, brought it about. And that cancellation of dh is not just a notational trick. That is a genuine reflection of what's going on with the tiny nudges that underpin everything we do with derivatives. So those are the three basic tools to have in your belt to handle derivatives of functions that combine a lot of smaller things. You've got the sum rule, the product rule, and the chain rule. And I'll be honest with you, there is a big difference between knowing what the chain rule is and what the product rule is, and actually being fluent with applying them in even the most hairy of situations. Watching videos, any videos, about the mechanics of calculus is never going to substitute for practicing those mechanics yourself, and building up the muscles to do these computations yourself. I really wish that I could offer to do that for you, but I'm afraid the ball is in your court, my friend, to seek out the practice. What I can offer, and what I hope I have offered, is to show you where these rules actually come from. To show that they're not just something to be memorized and hammered away, but they're natural patterns, things that you too could have discovered just by patiently thinking through what a derivative actually means. I've introduced a few derivative formulas, but a really important one that I left out was exponentials. So here, I want to talk about the derivatives of functions like 2 to the x, 7 to the x, and also to show why e to the x is arguably the most important of the exponentials. First of all, to get an intuition, let's just focus on the function 2 to the x. And let's think of that input as a time, t, maybe in days, and the output, 2 to the t, as a population size, perhaps of a particularly fertile band of pie creatures, which doubles every single day. And actually, instead of population size, which grows in discrete little jumps with each new baby pie creature, maybe let's think of 2 to the t as the total mass of the population. I think that better reflects the continuity of this function, don't you? So, for example, at time t equals 0, the total mass is 2 to the 0 equals 1 for the mass of one creature. At t equals 1 day, the population has grown to 2 to the 1 equals 2 creature masses. At day t equals 2, it's t squared, or 4, and in general, it just keeps doubling every day. For the derivative, we want dm dt, the rate at which this population mass is growing, thought of as a tiny change in the mass divided by a tiny change in time. And let's start by thinking of the rate of change over a full day, say between day 3 and day 4. Well, in this case, it grows from 8 to 16, so that's 8 new creature masses added over the course of one day. And notice, that rate of growth equals the population size at the start of the day. Between day 4 and day 5, it grows from 16 to 32, so that's a rate of 16 new creature masses per day, which again equals the population size at the start of the day. And in general, this rate of growth over a full day equals the population size at the start of that day. So it might be tempting to say that this means the derivative of 2 to the t equals itself, that the rate of change of this function at a given time t is equal to, well, the value of that function. And this is definitely in the right direction, but it's not quite correct. What we're doing here is making comparisons over a full day, considering the difference between 2 to the t plus 1 and 2 to the t. But for the derivative, we need to ask what happens for smaller and smaller changes. What's the growth over the course of a tenth of a day, a hundredth of a day, 1/1,000,000th of a day? This is why I had us think of the function as representing population mass, since it makes sense to ask about a tiny change in mass over a tiny fraction of a day, but it doesn't make as much sense to ask about the tiny change in a discrete population size per second. More abstractly, for a tiny change in time, dt, we want to understand the difference between 2 to the t plus dt and 2 to the t, all divided by dt. The change in the function per unit time, but now we're looking very narrowly around a given point in time, rather than over the course of a full day. And here's the thing. I would love if there was some very clear geometric picture that made everything that's about to follow just pop out. Some diagram where you could point to one value and say, see, that part, that is the derivative of 2 to the t. And if you know of one, please let me know. And while the goal here, as with the rest of the series, is to maintain a playful spirit of discovery, the type of play that follows will have more to do with finding numerical patterns rather than visual ones. So start by just taking a very close look at this term, 2 to the t plus dt. A core property of exponentials is that you can break this up as 2 to the t times 2 to the dt. That really is the most important property of exponents. If you add two values in that exponent, you can break up the output as a product of some kind. This is what lets you relate additive ideas, things like tiny steps in time, to multiplicative ideas, things like rates and ratios. I mean, just look at what happens here. After that move, we can factor out the term 2 to the t, which is now just multiplied by 2 to the dt minus 1, all divided by dt. And remember, the derivative of 2 to the t is whatever this whole expression approaches as dt approaches 0. And at first glance, that might seem like an unimportant manipulation. But a tremendously important fact is that this term on the right, where all of the dt stuff lives, is completely separate from the t term itself. It doesn't depend on the actual time where we started. You can go off to a calculator and plug in very small values for dt here. For example, maybe typing in 2 to the 0.001 minus 1 divided by 0.001. What you'll find is that for smaller and smaller choices of dt, this value approaches a very specific number, around 0.6931. Don't worry if that number seems mysterious. The central point is that this is some kind of constant. Unlike derivatives of other functions, all of the stuff that depends on dt is separate from the value of t itself. So the derivative of 2 to the t is just itself, but multiplied by some constant. And that should kind of make sense, because earlier it felt like the derivative for 2 to the t should be itself, at least when we were looking at changes over the course of a full day. And evidently, the rate of change for this function over much smaller timescales is not quite equal to itself, but it's proportional to itself, with this very peculiar proportionality constant of 0.6931. And there's not too much special about the number 2 here. If instead we had dealt with the function 3 to the t, the exponential property would also have led us to the conclusion that the derivative of 3 to the t is proportional to itself. But this time it would have had a proportionality constant 1.0986. And for other bases to your exponent, you can have fun trying to see what the various proportionality constants are, maybe seeing if you can find a pattern in them. For example, if you plug in 8 to the power of a very tiny number, minus 1, and divide by that same tiny number, what you'd find is that the relevant proportionality constant is around 2.079. And maybe, just maybe, you would notice that this number happens to be exactly 3 times the constant associated with the base for 2. So these numbers certainly aren't random, there is some kind of pattern. But what is it? What does 2 have to do with the number 0.6931? And what does 8 have to do with the number 2.079? Well, a second question that is ultimately going to explain these mystery constants is whether there's some base where that proportionality constant is 1, where the derivative of a to the power t is not just proportional to itself, but actually equal to itself. And there is! It's the special constant e, around 2.71828. In fact, it's not just that the number e happens to show up here. This is, in a sense, what defines the number e. If you ask, why does e of all numbers have this property, it's a little like asking, why does pi of all numbers happen to be the ratio of the circumference of a circle to its diameter? This is, at its heart, what defines this value. All exponential functions are proportional to their own derivative, but e alone is the special number so that that proportionality constant is 1, meaning e to the t actually equals its own derivative. One way to think of that is that if you look at the graph of e to the t, it has the peculiar property that the slope of a tangent line to any point on this graph equals the height of that point above the horizontal axis. The existence of a function like this answers the question of the mystery constants, and it's because it gives a different way to think about functions that are proportional to their own derivative. The key is to use the chain rule. For example, what is the derivative of e to the 3t? Well, you take the derivative of the outermost function, which due to this special nature of e is just itself, and then multiply by the derivative of that inner function, 3t, which is the constant, 3. Or rather than just applying a rule blindly, you could take this moment to practice the intuition for the chain rule that I talked through last video, thinking about how a slight nudge to t changes the value of 3t, and how that intermediate change nudges the final value of e to the 3t. Either way, the point is, e to the power of some constant times t is equal to that same constant times itself. And from here, the question of those mystery constants really just comes down to a certain algebraic manipulation. The number 2 can also be written as e to the natural log of 2. There's nothing fancy here. This is just the definition of the natural log. It asks the question, e to the what equals 2. So, the function 2 to the t is the same as the function e to the power of the natural log of 2 times t. And from what we just saw, combining the facts that e to the t is its own derivative with the chain rule, the derivative of this function is proportional to itself, with a proportionality constant equal to the natural log of 2. And indeed, if you go plug in the natural log of 2 to a calculator, you'll find that it's 0.6931, the mystery constant that we ran into earlier. And the same goes for all of the other bases. The mystery proportionality constant that pops up when taking derivatives is just the natural log of the base, the answer to the question, e to the what equals that base. In fact, throughout applications of calculus, you rarely see exponentials written as some base to a power t. Instead, you almost always write the exponential as e to the power of some constant times t. It's all equivalent. I mean, any function like 2 to the t or 3 to the t can also be written as e to some constant times t. At the risk of staying over-focused on the symbols here, I really want to emphasize that there are many, many ways to write down any particular exponential function. And when you see something written as e to some constant times t, that's a choice that we make to write it that way. And the number e is not fundamental to that function itself. What is special about writing exponentials in terms of e like this is that it gives that constant in the exponent a nice, readable meaning. Here, let me show you what I mean. All sorts of natural phenomena involve some rate of change that's proportional to the thing that's changing. For example, the rate of growth of a population actually does tend to be proportional to the size of the population itself, assuming there isn't some limited resource slowing things down. And if you put a cup of hot water in a cool room, the rate at which the water cools is proportional to the difference in temperature between the room and the water. Or, said a little differently, the rate at which that difference changes is proportional to itself. If you invest your money, the rate at which it grows is proportional to the amount of money there at any time. In all of these cases, where some variable's rate of change is proportional to itself, the function describing that variable over time is going to look like some kind of exponential. And even though there are lots of ways to write any exponential function, it's very natural to choose to express these functions as e to the power of some constant times t, since that constant carries a very natural meaning. It's the same as the proportionality constant between the size of the changing variable and the rate of change. Let me share with you something that I found particularly weird when I was a student first learning calculus. Let's say that you have a circle with radius 5 centered at the origin of the xy plane. This is something defined with the equation x squared plus y squared equals 5 squared. That is, all of the points on the circle are a distance 5 from the origin as encapsulated by the Pythagorean theorem, where the sum of the squares of the two legs on this triangle equal the square of the hypotenuse, 5 squared. And suppose that you want to find the slope of a tangent line to the circle, maybe at the point xy equals 3, 4. Now, if you're savvy with geometry, you might already know that this tangent line is perpendicular to the radius touching it at that point. But let's say you don't already know that. Or maybe you want a technique that generalizes to curves other than just circles. As with other problems about the slopes of tangent lines to curves, The key thought here is to zoom in close enough that the curve basically looks just like its own tangent line, and then ask about a tiny step along that curve. The y component of that little step is what you might call dy, and the x component is a little dx. So the slope that we want is the rise over run, dy divided by dx. But unlike other tangent slope problems in calculus, this curve is not the graph of a function. So we can't just take a simple derivative, asking about the size of some tiny nudge to the output of a function caused by some tiny nudge to the input. X is not an input, and y is not an output. They're both just interdependent values related by some equation. This is what's called an implicit curve. It's just the set of all points, x, y, that satisfies some property written in terms of the two variables, x and y. The procedure for how you actually find dy dx for curves like this is the thing that I found very weird as a calculus student. You take the derivative of both sides like this. For x squared, you write 2x times dx, and similarly y squared becomes 2y times dy. And then the derivative of that constant 5 squared on the right is just 0. Now, you can see why this feels a little strange, right? What does it mean to take the derivative of an expression that has multiple variables in it? And why is it that we're tacking on the little dy and the little dx in this way? But if you just blindly move forward with what you get, you can rearrange this equation and find an expression for dy divided by dx, which in this case comes out to be negative x divided by y. So, at the point with coordinates xy equals 3, 4, that slope would be negative 3 divided by 4, evidently. This strange process is called implicit differentiation. And don't worry, I have an explanation for how you can interpret taking a derivative of an expression with two variables like this. But first, I want to set aside this particular problem and show how it's connected to a different type of calculus problem, something called a related rates problem. Imagine a 5-meter long ladder held up against a wall where the top of the ladder starts 4 meters above the ground, which, by the Pythagorean theorem, means that that bottom is 3 meters away from the wall. And let's say it's slipping down in such a way that the top of the ladder is dropping at a rate of 1 meter per second. The question is, in that initial moment, what's the rate at which the bottom of the ladder is moving away from the wall? It's interesting, right? That distance from the bottom of the ladder to the wall is 100% determined by the distance from the top of the ladder to the floor. So we should have enough information to figure out how the rates of change for each of those values actually depend on each other. But it might not be entirely clear how exactly you relate those two. First things first, it's always nice to give names to the quantities that we care about. So let's label that distance from the top of the ladder to the ground y of t, written as a function of time because it's changing. Likewise, label the distance between the bottom of the ladder and the wall x of t. The key equation that relates these terms is the Pythagorean theorem. X of t squared plus y of t squared equals 5 squared. What makes that a powerful equation to use is that it's true at all points of time. Now, one way that you could solve this would be to isolate x of t, and then you figure out what y of t has to be based on that 1 meter per second drop rate, and you could take the derivative of the resulting function, dx dt, the rate at which x is changing with respect to time. And that's fine. It involves a couple layers of using the chain rule, and it'll definitely work for you. But I want to show a different way that you can think about the same problem. This left-hand side of the equation is a function of time, right? It just so happens to equal a constant, meaning the value evidently doesn't change while time passes, but it's still written as an expression dependent on time, which means we can manipulate it like any other function that has t as an input. In particular, we can take a derivative of this left-hand side, which is a way of saying, if I let a little bit of time pass, some small dt, which causes y to slightly decrease and x to slightly increase, how much does this expression change? On the one hand, we know that that derivative should be 0, since the expression is a constant, and constants don't care about your tiny nudges in time, they just remain unchanged. But on the other hand, what do you get when you compute this derivative? Well, the derivative of x of t squared is 2 times x of t times the derivative of x. That's the chain rule that I talked about last video. 2x dx represents the size of a change to x squared caused by some change to x, and then we're dividing out by dt. Likewise, the rate at which y of t squared is changing is 2 times y of t times the derivative of y. Now, evidently, this whole expression must be 0, and that's an equivalent way of saying that x squared plus y squared must not change while the latter moves. At the very start, time t equals 0, the height y of t is 4 meters, and that distance x of t is 3 meters. And since the top of the ladder is dropping at a rate of 1 meter per second, that derivative dy dt is negative 1 meters per second. Now, this gives us enough information to isolate the derivative, dx dt. And when you work it out, it comes out to be 4/3 meters per second. The reason I bring up this latter problem is that I want you to compare it to the problem of finding the slope of a tangent line to the circle. In both cases, we had the equation x squared plus y squared equals 5 squared. And in both cases, we ended up taking the derivative of each side of this expression. But for the latter question, these expressions were functions of time, so taking the derivative has a clear meaning. It's the rate at which the expression changes as time changes. But what makes the circle situation strange is that rather than saying that a small amount of time dt has passed, which causes x and y to change, the derivative just has these tiny nudges dx and dy just floating free, not tied to some other common variable, like time. Let me show you a nice way to think about this. Let's give this expression x squared plus y squared a name, maybe s. S is essentially a function of two variables. It takes every point xy on the plane and associates it with a number. For points on the circle, that number happens to be 25. If you stepped off the circle away from the center, that value would be bigger. For other points xy closer to the origin, that value would be smaller. Now, what it means to take a derivative of this expression, a derivative of s, is to consider a tiny change to both of these variables, some tiny change dx to x, and some tiny change dy to y. And not necessarily one that keeps you on the circle, by the way. It's just any tiny step in any direction of the xy plane. And from there, you ask, how much does the value of s change? And that difference, the difference in the value of s before the nudge and after the nudge, is what I'm writing as ds. For example, in this picture, we're starting off at a point where x equals 3 and where y equals 4. And let's just say that that step I drew has dx at negative 0.02 and dy at negative 0.01. Then the decrease in s, the amount that x squared plus y squared changes over that step, would be about 2 times 3 times negative 0.02 plus 2 times 4 times negative 0.01. That's what this derivative expression, 2x dx plus 2y dy, actually means. It's a recipe for telling you how much the value x squared plus y squared changes as determined by the point xy where you start and the tiny step dx dy that you take. And as with all things derivative, this is only an approximation, but it's one that gets truer and truer for smaller and smaller choices of dx and dy. The key point here is that when you restrict yourself to steps along the circle, you're essentially saying you want to ensure that this value of s doesn't change. It starts at a value of 25, and you want to keep it at a value of 25. That is, ds should be 0. So setting the expression 2x dx plus 2y dy equal to 0 is the condition under which one of these tiny steps actually stays on the circle. Again, this is only an approximation. Speaking more precisely, that condition is what keeps you on the tangent line of the circle, not the circle itself. But for tiny enough steps, those are essentially the same thing. Of course, there's nothing special about the expression x squared plus y squared equals 5 squared. It's always nice to think through more examples, so let's consider this expression sine of x times y squared equals x. This corresponds to a whole bunch of U-shaped curves on the plane. And those curves, remember, represent all of the points xy where the value of sine of x times y squared happens to equal the value of x. Now imagine taking some tiny step with components dx, dy, and not necessarily one that keeps you on the curve. Taking the derivative of each side of this equation is going to tell us how much the value of that side changes during the step. On the left side, the product rule that we talked through last video tells us that this should be left d right plus right d left. That is, sine of x times the change to y squared, which is 2y times dy, plus y squared times the change to sine of x, which is cosine of x times dx. The right side is simply x, so the size of a change to that value is exactly dx, right? Now setting these two sides equal to each other is a way of saying, whatever your tiny step with coordinates dx and dy is, if it's going to keep us on the curve, the values of both the left-hand side and the right-hand side must change by the same amount. That's the only way that this top equation can remain true. From there, depending on what problem you're trying to solve, you have something to work with algebraically. And maybe the most common goal is to try to figure out what dy divided by dx is. As a final example here, I want to show you how you can actually use this technique of implicit differentiation to figure out new derivative formulas. I've mentioned that the derivative of e to the x is itself. But what about the derivative of its inverse function, the natural log of x? Well, the graph of the natural log of x can be thought of as an implicit curve. It's all of the points xy on the plane where y happens to equal ln of x. It just happens to be the case that the x's and the y's of this equation aren't as intermingled as they were in our other examples. The slope of this graph, dy divided by dx, should be the derivative of ln of x, right? Well, to find that, first rearrange this equation, y equals ln of x, to be e to the y equals x. This is exactly what the natural log of x means. It's saying e to the what equals x. Since we know the derivative of e to the y, we can take the derivative of both sides here, effectively asking how a tiny step with components dx, dy changes the value of each one of these sides. To ensure that a step stays on the curve, the change to this left side of the equation, which is e to the y times dy, must equal the change to the right side, which in this case is just dx. Rearranging, that means that dy divided by dx, the slope of our graph, equals 1 divided by e to the y. And when we're on the curve, e to the y is, by definition, the same thing as x. So evidently, this slope is 1 divided by x. And of course, an expression for the slope of a graph of a function, written in terms of x like this, is the derivative of that function. So evidently, the derivative of ln of x is 1 divided by x. By the way, all of this is a little sneak peek into multivariable calculus, where you consider functions that have multiple inputs and how they change as you tweak those multiple inputs. The key, as always, is to have a clear image in your head of what tiny nudges are at play and how exactly they depend on each other. Next up, I'm going to be talking about limits and how they're used to formalize the idea of a derivative. The last several videos have been about the idea of a derivative, and before moving on to integrals, I want to take some time to talk about limits. To be honest, the idea of a limit is not really anything new. If you know what the word approach means, you pretty much already know what a limit is. You could say that it's a matter of assigning fancy notation to the intuitive idea of one value that just gets closer to another. But there actually are a few reasons to devote a full video to this topic. For one thing, it's worth showing how the way that I've been describing derivatives so far lines up with the formal definition of a derivative as it's typically presented in most courses and textbooks. I want to give you a little confidence that thinking in terms of dx and df as concrete, non-zero nudges is not just some trick for building intuition. It's actually backed up by the formal definition of a derivative in all of its rigor. I also want to shed light on what exactly mathematicians mean when they say approach, in terms of something called the epsilon delta definition of limits. Then we'll finish off with a clever trick for computing limits called L'Hopital's rule. So, first things first, let's take a look at the formal definition of the derivative. As a reminder, when you have some function f of x, to think about its derivative at a particular input, maybe x equals 2, you start by imagining nudging that input some little dx away, and looking at the resulting change to the output, df. The ratio, df divided by dx, which can be nicely thought of as the rise over run slope between the starting point on the graph and the nudged point, is almost what the derivative is. The actual derivative is whatever this ratio approaches as dx approaches 0. And just to spell out a little of what's meant there, that nudge to the output, df, is the difference between f at the starting input plus dx and f at the starting input, the change to the output caused by dx. To express that you want to find what this ratio approaches as dx approaches 0, you write lim for limit with dx arrow 0 below it. Now, you'll almost never see terms with a lowercase d, like dx, inside a limit expression like this. Instead, the standard is to use a different variable, something like delta x, or commonly h for whatever reason. The way I like to think of it is that terms with this lowercase d in the typical derivative expression have built into them this idea of a limit, the idea that dx is supposed to eventually go to 0. So in a sense, this left-hand side here, df over dx, the ratio we've been thinking about for the past few videos, is just shorthand for what the right-hand side here spells out in more detail, writing out exactly what we mean by df, and writing out this limit process explicitly. And this right-hand side here is the formal definition of a derivative, as you would commonly see it in any calculus textbook. And if you'll pardon me for a small rant here, I want to emphasize that nothing about this right-hand side references the paradoxical idea of an infinitely small change. The point of limits is to avoid that. This value h is the exact same thing as the dx I've been referencing throughout the series. It's a nudge to the input of f with some non-zero, finitely small size, like 0.001. It's just that we're analyzing what happens for arbitrarily small choices of h. In fact, the only reason that people introduce a new variable name into this formal definition, rather than just, using dx, is to be super extra clear that these changes to the input are just ordinary numbers that have nothing to do with infinitesimals. Because the thing is, there are others who like to interpret this dx as an infinitely small change, whatever that would mean. Or to just say that dx and df are nothing more than symbols that we shouldn't take too seriously. But by now in the series, you know I'm not really a fan of either of those views. I think you can, and should, interpret dx as a concrete, finitely small nudge, just so long as you remember to ask what happens when that thing approaches 0. For one thing, and I hope the past few videos have helped convince you of this, that helps to build stronger intuition for where the rules of calculus actually come from. But it's not just some trick for building intuitions. Everything I've been saying about derivatives, with this concrete, finitely small nudge philosophy, is just a translation of this formal definition we're staring at right now. So, long story short, the big fuss about limits is that they let us avoid talking about infinitely small changes, by instead asking what happens as the size of some small change to our variable approaches 0. And this brings us to goal number 2, understanding exactly what it means for one value to approach another. For example, consider the function 2 plus h cubed minus 2 cubed, all divided by h. This happens to be the expression that pops out when you unravel the definition of a derivative of x cubed, evaluated at x equals 2, but let's just think of it as any old function with an input h. Its graph is this nice continuous-looking parabola, which would make sense because it's a cubic term divided by a linear term. But actually, if you think about what's going on at h equals 0, plugging that in, you would get 0 divided by 0, which is not defined. So really, this graph has a hole at that point, and you have to kind of exaggerate to draw that hole, often with a little empty circle like this. But keep in mind, the function is perfectly well defined for inputs as close to 0 as you want. And wouldn't you agree that as h approaches 0, the corresponding output, the height of this graph, approaches 12? And it doesn't matter which side you come at it from. That limit of this ratio, as h approaches 0, is equal to 12. But imagine that you are a mathematician inventing calculus, and someone skeptically asks you, well, what exactly do you mean by approach? That would be kind of an annoying question. I mean, come on, we all know what it means for one value to get closer to another. But let's start thinking about ways that you might be able to answer that person, completely unambiguously. For a given range of inputs within some distance of 0, excluding the forbidden point 0 itself, look at all of the corresponding outputs, all possible heights of the graph above that range. As the range of input values closes in more and more tightly around 0, that range of output values closes in more and more closely around 12. And importantly, the size of that range of output values can be made as small as you want. As a counterexample, consider a function that looks like this, which is also not defined at 0, but it kind of jumps up at that point. When you approach h equals 0 from the right, the function approaches the value 2. But as you come at it from the left, it approaches 1. Since there's not a single clear, unambiguous value that this function approaches as h approaches 0, the limit is simply not defined at that point. One way to think of this is that when you look at any range of inputs around 0 and consider the corresponding range of outputs, as you shrink that input range, the corresponding outputs don't narrow in on any specific value. Instead, those outputs straddle a range that never shrinks smaller than 1, even as you make that input range as tiny as you could imagine. And this perspective of shrinking an input range around the limiting point and seeing whether or not you're restricted in how much that shrinks the output range leads to something called the epsilon delta definition of limits. Now, I should tell you, you could argue that this is needlessly heavy duty for an introduction to calculus. Like I said, if you know what the word approach means, you already know what a limit means. There's nothing new on the conceptual level here. But this is an interesting glimpse into the field of real analysis, and it gives you a taste for how mathematicians make the intuitive ideas of calculus a little more airtight and rigorous. You've already seen the main idea here. When a limit exists, you can make this output range as small as you want. But when the limit doesn't exist, that output range cannot get smaller than some particular value, no matter how much you shrink the input range around the limiting input. Let's phrase that same idea, but a little more precisely, maybe in the context of this example where the limiting value was 12. Think about any distance away from 12, where for some reason it's common to use the Greek letter epsilon to denote that distance. And the intent here is going to be that this distance epsilon is as small as you want. What it means for the limit to exist is that you will always be able to find a range of inputs around our limiting point, some distance delta around 0, so that any input within delta of 0 corresponds to an output within a distance epsilon of 12. And the key point here is that that's true for any epsilon, no matter how small. You'll always be able to find the corresponding delta. In contrast, when a limit does not exist, as in this example here, you can find a sufficiently small epsilon, like 0.4, so that no matter how small you make your range around 0, no matter how tiny delta is, the corresponding range of outputs is just always too big. There is no limiting output where everything is within a distance epsilon of that output. So far, this is all pretty theory heavy, don't you think? Limits being used to formally define the derivative, and then epsilons and deltas being used to rigorously define the limit itself. So let's finish things off here with a trick for actually computing limits. For instance, let's say for some reason you were studying the function sine of pi times x divided by x squared minus 1. Maybe this was modeling some kind of dampened oscillation. When you plot a bunch of points to graph this, it looks pretty continuous. But there's a problematic value at x equals 1. When you plug that in, sine of pi is, well, 0, and the denominator also comes out to 0. So the function is actually not defined at that input, and the graph should really have a hole there. This also happens, by the way, at x equals -1, but let's just focus our attention on a single one of these holes for now. The graph certainly does seem to approach a distinct value at that point, wouldn't you say? So you might ask, how exactly do you find what output this approaches as x approaches 1, since you can't just plug in 1? Well, one way to approximate it would be to plug in a number that's just really close to 1, like 1.00001. Doing that, you'd find that this should be a number around -1.57. But is there a way to know precisely what it is? Some systematic process to take an expression like this one, that looks like 0 divided by 0 at some input, and ask what is its limit as x approaches that input? After limits so helpfully let us write the definition for derivatives, derivatives can actually come back here and return the favor to help us evaluate limits. Let me show you what I mean. Here's what the graph of sine of pi times x looks like. And here's what the graph of x squared minus 1 looks like. That's kind of a lot to have up on the screen, but just focus on what's happening around x equals 1. The point here is that sine of pi times x and x squared minus 1 are both 0 at that point. They both cross the x-axis. In the same spirit as plugging in a specific value near 1, like 1.00001, let's zoom in on that point and consider what happens just a tiny nudge dx away from it. The value sine of pi times x is bumped down, and the value of that nudge, which was caused by the nudge dx to the input, is what we might call d sine of pi x. And from our knowledge of derivatives, using the chain rule, that should be around cosine of pi times x times pi times dx. Since the starting value was x equals 1, we plug in x equals 1 to that expression. In other words, the amount that this sine of pi times x graph changes is roughly proportional to dx, with a proportionality constant equal to cosine of pi times pi. And cosine of pi, if we think back to our trig knowledge, is exactly -1. So we can write this whole thing as negative pi times dx. Similarly, the value of the x squared minus 1 graph changes by some dx squared minus 1. And taking the derivative, the size of that nudge should be 2x times dx. Again, we were starting at x equals 1, so we plug in x equals 1 to that expression, meaning the size of that output nudge is about 2 times 1 times dx. What this means is that for values of x which are just a tiny nudge dx away from 1, the ratio, sine of pi x divided by x squared minus 1, is approximately negative pi times dx divided by 2 times dx. The dx's here cancel out, so what's left is negative pi over 2. And importantly, those approximations get more and more accurate for smaller and smaller choices of dx, right? So this ratio, negative pi over 2, actually tells us the precise limiting value as x approaches 1. And remember, what that means is that the limiting height on our original graph is evidently exactly negative pi over 2. Now, what happened there is a little subtle, so I want to go through it again, but this time a little more generally. Instead of these two specific functions, which are both equal to 0 at x equals 1, think of any two functions, f of x and g of x, which are both 0 at some common value, x equals a. The only constraint is that these have to be functions where you're able to take a derivative of them at x equals a, which means that they each basically look like a line when you zoom in close enough to that value. Now, even though you can't compute f divided by g at this trouble point, since both of them equal 0, you can ask about this ratio for values of x really close to a, the limit as x approaches a. And it's helpful to think of those nearby inputs as just a tiny nudge, dx, away from a. The value of f at that nudged point is approximately its derivative, df over dx, evaluated at a, times dx. Likewise, the value of g at that nudged point is approximately the derivative of g, evaluated at a, times dx. So near that trouble point, the ratio between the outputs of f and g is actually about the same as the derivative of f at a times dx divided by the derivative of g at a times dx. Those dx's cancel out, so the ratio of f and g near a is about the same as the ratio between their derivatives. Because each of those approximations gets more and more accurate for smaller and smaller nudges, this ratio of derivatives gives the precise value for the limit. This is a really handy trick for computing a lot of limits. Whenever you come across some expression that seems to equal 0 divided by 0 when you plug in some particular input, just try taking the derivative of the top and bottom expressions and plugging in that same treble input. This clever trick is called L'Hopital's rule. Interestingly, it was actually discovered by Johann Bernoulli, but L'Hopital was this wealthy dude who essentially paid Bernoulli for the rights to some of his mathematical discoveries. Academia is weird back then, but hey, in a very literal way, it pays to understand these tiny nudges. Now, right now, you might be remembering that the definition of a derivative for a given function comes down to computing the limit of a certain fraction that looks like 0 divided by 0. So you might think that L'Hopital's rule could give us a handy way to discover new derivative formulas. But that would actually be cheating, since presumably you don't know what the derivative of the numerator here is. When it comes to discovering derivative formulas, something that we've been doing a fair amount this series, there is no systematic plug-and-chug method. But that's a good thing. Whenever creativity is needed to solve problems like these, it's a good sign that you're doing something real, something that might give you a powerful tool to solve future problems. And speaking of powerful tools, up next I'm going to be talking about what an integral is, as well as the fundamental theorem of calculus. And this is another example of where limits can be used to help give a clear meaning to a pretty delicate idea that flirts with infinity. This guy, Grothendieck, is somewhat of a mathematical idol to me. And I just love this quote, don't you? Too often in math, we dive into showing that a certain fact is true with a long series of formulas before stepping back and making sure that it feels reasonable, and preferably obvious, at least at an intuitive level. In this video, I want to talk about integrals, and the thing that I want to become almost obvious is that they are an inverse of derivatives. Here, we're just going to focus on one example, which is a kind of dual to the example of a moving car that I talked about in chapter 2 of the series, introducing derivatives. Then in the next video, we're going to see how this same idea generalizes, but to a couple other contexts. Imagine that you're sitting in a car, and you can't see out the window. All you see is the speedometer. At some point, the car starts moving, speeds up, and then slows back down to a stop, all over the course of 8 seconds. The question is there a nice way to figure out how far you've traveled during that time based only on your view of the speedometer? Or better yet, can you find a distance function, s of t, that tells you how far you've traveled after a given amount of time, t, somewhere between 0 and 8 seconds? Let's say that you take note of the velocity at every second, and you make a plot over time that looks something like this. And maybe you find that a nice function to model that velocity over time in meters per second is v of t equals t times 8 minus t. You might remember, in chapter 2 of the series, we were looking at the opposite situation, where you knew what a distance function was, s of t, and you wanted to figure out the velocity function from that. There, I showed how the derivative of a distance versus time function gives you a velocity versus time function. So in our current situation, where all we know is velocity, it should make sense that finding a distance versus time function is going to come down to asking what function has a derivative of t times 8 minus t. This is often described as finding the antiderivative of a function. And indeed, that's what we'll end up doing. And you could even pause right now and try that. But first, I want to spend the bulk of this video showing how this question is related to finding the area bounded by the velocity graph. Because that helps to build an intuition for a whole class of problems, things called integral problems in math and science. To start off, notice that this question would be a lot easier if the car was just moving at a constant velocity, right? In that case, you could just multiply the velocity, in meters per second, times the amount of time that has passed, in seconds, and that would give you the number of meters traveled. And notice, you can visualize that product, that distance, as an area. And if visualizing distance as area seems kind of weird, I'm right there with you. It's just that on this plot, where the horizontal direction has units of seconds, and the vertical direction has units of meters per second, units of area just very naturally correspond to meters. But what makes our situation hard is that velocity is not constant. It's incessantly changing at every single instant. It would even be a lot easier if it only ever changed at a handful of points. maybe staying static for the first second, and then suddenly discontinuously jumping to a constant 7 meters per second for the next second, and so on, with discontinuous jumps to portions of constant velocity. That would make it uncomfortable for the driver. In fact, it's actually physically impossible, but it would make your calculations a lot more straightforward. You could just compute the distance traveled on each interval by multiplying the constant velocity on that interval by the change in time, and then just add all of those up. So what we're going to do is approximate the velocity function as if it was constant on a bunch of intervals. And then, as is common in calculus, we'll see how refining that approximation leads us to something more precise. Here, let's make this a little more concrete by throwing in some numbers. Chop up the time axis between 0 and 8 seconds into many small intervals, each with some little width dt, something like 0.25 seconds. Now consider one of those intervals, like the one between t equals 1 and 1.25. In reality, the car speeds up from 7 meters per second to about 8.4 meters per second during that time. And you could find those numbers just by plugging in t equals 1 and t equals 1.25 to the equation for velocity. What we want to do is approximate the car's motion as if its velocity was constant on that interval. Again, the reason for doing that is we just don't really know how to handle situations other than constant velocity ones. You could choose this constant to be anything between 7 and 8.4. It actually doesn't matter. All that matters is that our sequence of approximations, whatever they are, gets better and better as dt gets smaller and smaller. That treating this car's journey as a bunch of discontinuous jumps in speed between portions of constant velocity becomes a less wrong reflection of reality as we decrease the time between those jumps. So, for convenience, on an interval like this, let's just approximate the speed with whatever the true car's velocity is at the start of that interval, the height of the graph above the left side, which in this case is 7. So in this example interval, according to our approximation, the car moves 7 meters per second times 0.25 seconds. That's 1.75 meters, and it's nicely visualized as the area of this thin rectangle. In truth, that's a little under the real distance traveled, but not by much. And the same goes for every other interval. The approximated distance is v of t times dt. It's just that you'd be plugging in a different value for t at each one of these, giving a different height for each rectangle. I'm going to write out an expression for the sum of the areas of all those rectangles in kind of a funny way. Take this symbol here, which looks like a stretched S for sum, and then put a 0 at its bottom and an 8 at its top, to indicate that we'll be ranging over time steps between 0 and 8 seconds. And as I said, the amount we're adding up at each time step is v of t times dt. Two things are implicit in this notation. First of all, that value dt plays two separate roles. Not only is it a factor in each quantity that we're adding up, it also indicates the spacing between each sampled time step. So when you make dt smaller and smaller, even though it decreases the area of each rectangle, it increases the total number of rectangles whose areas we're adding up, because if they're thinner, it takes more of them to fill that space. And second, the reason we don't use the usual sigma notation to indicate a sum is that this expression is technically not any particular sum for any particular choice of dt. It's meant to express whatever that sum approaches as dt approaches 0. And as you can see, what that approaches is the area bounded by this curve and the horizontal axis. Remember, smaller choices of dt indicate closer approximations for the original question. How far does the car actually go? So this limiting value for the sum, the area under this curve, gives us the precise answer to the question in full unapproximated precision. Now tell me that's not surprising. We had this pretty complicated idea of approximations that can involve adding up a huge number of very tiny things. And yet, the value that those approximations approach can be described so simply. It's just the area underneath this curve. This expression is called an integral of v of t, since it brings all of its values together. It integrates them. Now at this point, you could say, how does this help? you've just reframed one hard question, finding how far the car has traveled, into an equally hard problem, finding the area between this graph and the horizontal axis. And you'd be right. If the velocity-distance duo was the only thing that we cared about, most of this video, with all of the area under a curve nonsense, would be a waste of time. We could just skip straight ahead to finding an antiderivative. But finding the area between a function's graph and the horizontal axis is somewhat of a common language for many disparate problems that can be broken down and approximated as the sum of a large number of small things. You'll see more in the next video, but for now I'll just say in the abstract that understanding how to interpret and how to compute the area under a graph is a very general problem-solving tool. In fact, the first video of this series already covered the basics of how this works. But now that we have more of a background with derivatives, we can actually take this idea to its completion. For our velocity example, think of this right endpoint as a variable, capital T. So we're thinking of this integral of the velocity function between 0 and t, the area under this curve between those inputs, as a function, where the upper bound is the variable. That area represents the distance the car has traveled after t seconds, right? So in reality, this is a distance versus time function, s of t. Now ask yourself, what is the derivative of that function? On the one hand, a tiny change in distance over a tiny change in time, that's velocity. That is what velocity means. But there's another way to see this, purely in terms of this graph and this area, which generalizes a lot better to other integral problems. A slight nudge of dt to the input causes that area to increase, some little ds represented by the area of this sliver. The height of that sliver is the height of the graph at that point, v of t, and its width is dt. And for small enough dt, we can basically consider that sliver to be a rectangle, so this little bit of added area, ds, is approximately equal to v of t times dt. And because that's an approximation that gets better and better for smaller dt, the derivative of that area function, ds dt, at this point equals vt, the value of the velocity function at whatever time we started on. And that right there, that's a super general argument. The derivative of any function giving the area under a graph like this is equal to the function for the graph itself. So, if our velocity function is t times 8 minus t, what should s be? What function of t has a derivative of t times 8 minus t? It's easier to see if we expand this out, writing it as 8t minus t squared, and then we can just take each part one at a time. What function has a derivative of 8 times t? Well, we know that the derivative of t squared is 2t, so if we just scale that up by a factor of 4, we can see that the derivative of 4t squared is 8t. And for that second part, what kind of function do you think might have negative t squared as a derivative? Well, using the power rule again, we know that the derivative of a cubic term, t cubed, gives us a square term, 3t squared. So if we just scale that down by a third, the derivative of 1/3 t cubed is exactly t squared. And then making that negative, you'd see that negative 1/3 t cubed has a derivative of negative t squared. Therefore, the antiderivative of our function, 8t minus t squared, is 4t squared minus 1/3 t cubed. But there's a slight issue here. We could add any constant we want to this function, and its derivative is still going to be 8t minus t squared. The derivative of a constant just always goes to 0. And if you were to graph s of t, you could think of this in the sense that moving a graph of a distance function up and down does nothing to affect its slope at every input. So in reality, there's actually infinitely many different possible antiderivative functions, and every one of them looks like 4t squared minus 1/3 t cubed plus c, for some constant c. But there is one piece of information that we haven't used yet that's going to let us zero in on which antiderivative to use: the lower bound of the integral. This integral has to be 0 when we drag that right endpoint all the way to the left endpoint, right? The distance traveled by the car between 0 seconds and 0 seconds is, well, 0. So, as we found, the area as a function of capital T is an antiderivative for the stuff inside. And to choose what constant to add to this expression, what you do is subtract off the value of that antiderivative function at the lower bound. If you think about it for a moment, that ensures that the integral from the lower bound to itself will indeed be 0. As it so happens, when you evaluate the function we have right here at t equals 0, you get 0. So in this specific case, you actually don't need to subtract anything off. For example, the total distance traveled during the full 8 seconds is this expression evaluated at t equals 8, which is about 85.33, minus 0. So the answer as a whole is just 85.33. But a more typical example would be something like the integral between 1 and 7. That's the area pictured right here, and it represents the distance traveled between 1 second and 7 seconds. What you do is evaluate the antiderivative we found at the top bound, 7, and then subtract off its value at that bottom bound, 1. And notice, by the way, it doesn't matter which antiderivative we chose here. If for some reason it had a constant added to it, like 5, that constant would just cancel out. More generally, anytime you want to integrate some function, and remember, you think of that as adding up values f of x times dx for inputs in a certain range, and then asking, what does that sum approach as dx approaches 0? The first step to evaluating that integral is to find an antiderivative, some other function, capital F, whose derivative is the thing inside the integral. Then, the integral equals this antiderivative evaluated at the top bound minus its value at the bottom bound. And this fact right here that you're staring at is the fundamental theorem of calculus. And I want you to appreciate something kind of crazy about this fact. The integral, the limiting value for the sum of all of these thin rectangles, takes into account every single input on the continuum from the lower bound to the upper bound. That's why we use the word integrate. It brings them all together. And yet, to actually compute it using an antiderivative, you only look at 2 inputs, the top bound and the bottom bound. It almost feels like cheating. Finding the antiderivative implicitly accounts for all of the information needed to add up the values between those 2 bounds. That's just crazy to me. This idea is deep, and there's a lot packed into this whole concept. So let's just recap everything that just happened, shall we? We wanted to figure out how far a car goes just by looking at the speedometer. And what makes that hard is that velocity is always changing. If you approximate velocity to be constant on multiple different intervals, you could figure out how far the car goes on each interval just with multiplication, and then add all of those up. Better and better approximations for the original problem correspond to collections of rectangles whose aggregate area is closer and closer to being the area under this curve between the start time and the end time. So that area under the curve is actually the precise distance traveled for the true nowhere constant velocity function. If you think of that area as a function itself, with a variable right endpoint, you can deduce that the derivative of that area function must equal the height of the graph at every point. And that's really the key right there. It means that to find a function giving this area, you ask, what function has v of t as a derivative? There are actually infinitely many antiderivatives of a given function, since you can always just add some constant without affecting the derivative. So you account for that by subtracting off the value of whatever antiderivative function you choose at the bottom bound. By the way, one important thing to bring up before we leave is the idea of negative area. What if the velocity function was negative at some point, meaning the car goes backwards? It's still true that a tiny distance traveled, ds, on a little time interval is about equal to the velocity at that time multiplied by the tiny change in time. It's just that the number you'd plug in for velocity would be negative, so the tiny change in distance is negative. In terms of our thin rectangles, if a rectangle goes below the horizontal axis, like this, its area represents a bit of distance traveled backwards, So if what you want in the end is to find a distance between the car's start point and its end point, this is something you're going to want to subtract. And that's generally true of integrals. Whenever a graph dips below the horizontal axis, the area between that portion of the graph and the horizontal axis is counted as negative. And what you'll commonly hear is that integrals don't measure area per se, they measure the signed area between the graph and the horizontal axis. Next up, I'm going to bring up more context where this idea of an integral and area under curves comes up, along with some other intuitions for this fundamental theorem of calculus. Here, I want to discuss one common type of problem where integration comes up, finding the average of a continuous variable. This is a perfectly useful thing to know in its own right, but what's really neat is that it can give us a completely different perspective for why integrals and derivatives are inverses of each other. To start, take a look at the graph of sine of x between 0 and pi, which is half of its period. What is the average height of this graph on that interval? It's not a useless question. All sorts of cyclic phenomena in the world are modeled using sine waves. For example, the number of hours that the sun is up per day, as a function of what day of the year it is, follows a sine wave pattern. So if you wanted to predict, say, the average effectiveness of solar panels in summer months versus winter months, you'd want to be able to answer a question like this. What is the average value of that sine function over half of its period? Whereas a case like this is going to have all sorts of constants mucking up the function, you and I are just going to focus on a pure, unencumbered sine of x function. But the substance of the approach would be totally the same in any other application. It's kind of a weird question to think about though, isn't it? The average of a continuous variable. Usually with averages we think of a finite number of variables, where you can add them all up and divide that sum by how many there are. But there are infinitely many values of sine of x between 0 and pi, and it's not like we can just add up all of those numbers and divide by infinity. Now, this sensation actually comes up a lot in math, and it's worth remembering, where you have this vague sense that what you want to do is add together infinitely many values associated with a continuum, even though that doesn't really make sense. And almost always, when you get that sense, the key is going to be to use an integral somehow. And to think through exactly how, a good first step is usually to just approximate your situation with some kind of finite sum. In this case, imagine sampling a finite number of points evenly spaced along this range. Since it's a finite sample, you can find the average by just adding up all of the heights sine of x at each one of these, and then dividing that sum by the number of points that you sampled, right? And presumably, if the idea of an average height among all infinitely many points is going to make any sense at all, the more points we sample, which would involve adding up more and more heights, the closer the average of that sample should be to the actual average of the continuous variable. And this should feel at least somewhat related to taking an integral of sine of x between 0 and pi, even if it might not be exactly clear how the two ideas match up. For that integral, remember, you also think of a sample of inputs on this continuum, but instead of adding the height, sine of x at each one, and dividing by how many there are, you add up sine of x times dx, where dx is the spacing between the samples. That is, you're adding up little areas, not heights. And technically, the integral is not quite this sum. It's whatever that sum approaches as dx approaches 0. But it is actually quite helpful to reason with respect to one of these finite iterations, where we're looking at a concrete size for dx and some specific number of rectangles. So what you want to do here is reframe this expression for the average, this sum of the heights divided by the number of sampled points, in terms of dx, the spacing between samples. And now, if I tell you that the spacing between these points is, say, 0.1, and you know that they range from 0 to pi, can you tell me how many there are? Well, you can take the length of that interval, pi, and divide it by the length of the space between each sample. If it doesn't go in perfectly evenly, you would have to round down to the nearest integer, but as an approximation, this is completely fine. So if we write that spacing between samples as dx, the number of samples is pi divided by dx. And when we substitute that into our expression up here, you can rearrange it, putting that dx up top and distributing it into the sum. But think about what it means to distribute that dx up top. It means that the terms you're adding up will look like sine of x times dx for the various inputs x that you're sampling. So that numerator looks exactly like an integral expression. And so for larger and larger samples of points, this average will approach the actual integral of sine of x between 0 and pi, all divided by the length of that interval, pi. In other words, the average height of this graph is this area divided by its width. On an intuitive level, and just thinking in terms of units, that feels pretty reasonable, doesn't it? Area divided by width gives you an average height. So, with this expression in hand, let's actually solve it. As we saw last video, to compute an integral, you need to find an antiderivative of the function inside the integral, some other function whose derivative is sine of x. And if you're comfortable with derivatives of trig functions, you know that the derivative of cosine is negative sine. So if you just negate that, negative cosine is the function we want, the antiderivative of sine. And to gut check yourself on that, look at this graph of negative cosine. At 0, the slope is 0. And then it increases up to some maximum slope at pi halves, and then goes back down to 0 at pi. And in general, its slope does indeed seem to match the height of the sine graph at every point. So what do we have to do to evaluate the integral of sine between 0 and pi? Well, we evaluate this antiderivative at the upper bound and subtract off its value at the lower bound. More visually, that is the difference in the height of this negative cosine graph above pi and its height at 0. And as you can see, that change in height is exactly 2. That's kind of interesting, isn't it? That the area under this sine graph turns out to be exactly 2. So the answer to our average height problem, this integral divided by the width of the region, evidently turns out to be 2 divided by pi, which is around 0.64. I promised at the start that this question of finding the average of a function offers an alternate perspective on why integrals and derivatives are inverses of each other, why the area under one graph has anything to do with the slope of another graph. Notice how finding this average value, 2 divided by pi, came down to looking at the change in the antiderivative, negative cosine x, over the input range, divided by the length of that range. And another way to think about that fraction is as the rise over run slope between the point of the antiderivative graph below 0 and the point of that graph above pi. And now think about why it might make sense that this slope would represent an average value of sine of x on that region. Well, by definition, sine of x is the derivative of this antiderivative graph. It gives us the slope of negative cosine at every point. So another way to think about the average value of sine of x is as the average slope over all tangent lines here between 0 and pi. And when you view things like that, doesn't it make a lot of sense that the average slope of a graph over all of its points in a certain range should equal the total slope between the start and end points? To digest this idea, it helps to think about what it looks like for a general function. For any function, f of x, if you want to find its average value on some interval, say between a and b, what you do is take the integral of f on that interval divided by the width of that interval, b minus a. You can think of this as the area under the graph divided by its width, or more accurately, it is the signed area of that graph, since any area below the x-axis is counted as negative. And it's worth taking a moment to remember what this area has to do with the usual notion of a finite average, where you add up many numbers and divide by how many there are. When you take some sample of points spaced out by dx, the number of samples is about equal to the length of the interval divided by dx. So if you add up the values of f of x at each sample, and divide by the total number of samples, it's the same as adding up the product, f of x times dx, and dividing by the width of the entire interval. The only difference between that and the integral is that the integral asks what happens as dx approaches 0. But that just corresponds with samples of more and more points that approximate the true average increasingly well. Now, for any integral, evaluating it comes down to finding an antiderivative of f of x, commonly denoted capital F of x. What we want is the change to this antiderivative between a and b, capital F of b minus capital F of a, which you can think of as the change in height of this new graph between the two bounds. I've conveniently chosen an antiderivative that passes through 0 at the lower bound here, but keep in mind, you can freely shift this up and down, adding whatever constant you want to it, and it would still be a valid antiderivative. So the solution to the average problem is the change in the height of this new graph divided by the change to the x value between a and b. In other words, it is the slope of the antiderivative graph between the two endpoints. And again, when you stop to think about it, that should make a lot of sense, because little f of x gives us the slope of the tangent line to this graph at each point. After all, it is by definition the derivative of capital F. So, why are antiderivatives the key to solving integrals? Well, my favorite intuition is still the one that I showed last video, but a second perspective is that when you reframe the question of finding an average of a continuous value as instead finding the average slope of a bunch of tangent lines, it lets you see the answer just by comparing endpoints, rather than having to actually tally up all of the points in between. In the last video, I described a sensation that should bring integrals to your mind, namely, if you feel like the problem you're solving could be approximated by breaking it up somehow and adding up a large number of small things. And here, I want you to come away recognizing a second sensation that should also bring integrals to your mind. If ever there's some idea that you understand in a finite context, and which involves adding up multiple values, like taking the average of a bunch of numbers, and if you want to generalize that idea to apply to an infinite continuous range of values, try seeing if you can phrase things in terms of an integral. It's a feeling that comes up all the time, especially in probability, and it's definitely worth remembering. In the next chapter about Taylor series, I make frequent reference to higher order derivatives. And if you're already comfortable with second derivatives, third derivatives, and so on, great! Feel free to just skip ahead to the main event now. You won't hurt my feelings. But somehow, I've managed not to bring up higher order derivatives at all so far in this series. So for the sake of completeness, I thought I'd give you this little footnote just to go over them very quickly. I'll focus mainly on the second derivative, showing what it looks like in the context of graphs and motion, and leave you to think about the analogies for higher orders. Given some function, f of x, the derivative can be interpreted as the slope of this graph above some point, right? A steep slope means a high value for the derivative, a downward slope means a negative derivative. So the second derivative, whose notation I'll explain in just a moment, is the derivative of the derivative, meaning it tells you how that slope is changing. The way to see that at a glance is to think about how the graph of f of x curves. At points where it curves upwards, like this, the slope is increasing, and that means the second derivative is positive. At points where it's curving downwards, the slope is decreasing, so the second derivative is negative. For example, a graph like this one has a very positive second derivative at the point 4, since the slope is rapidly increasing around that point. Whereas a graph like this one still has a positive second derivative at the same point, but it's smaller. I mean, the slope only increases slowly. At points where there's not really any curvature, the second derivative is just 0. As far as notation goes, you could try writing it like this, indicating some small change to the derivative function divided by some small change to x, where, as always, the use of this letter d suggests that what you really want to consider is what this ratio approaches as dx, both dx's in this case, approach 0. That's pretty awkward and clunky, so the standard is to abbreviate this as d squared f divided by dx squared. And even though it's not terribly important for getting an intuition for the second derivative, I think it might be worth showing you how you can read this notation. To start off, think of some input to your function, and then take 2 small steps to the right, each one with the size of dx. I'm choosing rather big steps here so that we'll be able to see what's going on, but in principle, keep in the back of your mind that dx should be rather tiny. The first step causes some change to the function, which I'll call df1, and the second step causes some similar but possibly slightly different change, which I'll call df2. The difference between these changes, the change in how the function changes, is what we'll call ddf. You should think of this as really small, typically proportional to the size of dx squared. So if, for example, you substituted in 0.01 for dx, you would expect this ddf to be about proportional to 0.0001. And the second derivative is the size of this change to the change divided by the size of dx squared. Or more precisely, it's whatever that ratio approaches as dx approaches 0. Even though it's not like this letter d is a variable being multiplied by f, for the sake of more compact notation, you'd write it as d squared f divided by dx squared, and you don't typically bother with any parentheses on the bottom. Maybe the most visceral understanding of the second derivative is that it represents acceleration. Given some movement along a line, suppose you have some function that records the distance traveled versus time. Maybe its graph looks something like this, steadily increasing over time. Then its derivative tells you velocity at each point in time, right? For example, the graph might look like this bump, increasing up to some maximum and then decreasing back to 0. So the second derivative tells you the rate of change for the velocity, which is the acceleration at each point in time. In this example, the second derivative is positive for the first half of the journey, which indicates speeding up. That's the sensation of being pushed back into your car seat, or rather having the car seat push you forward. A negative second derivative indicates slowing down, negative acceleration. The third derivative, and this is not a joke, is called jerk. So if the jerk is not 0, it means that the strength of the acceleration itself is changing. One of the most useful things about higher order derivatives is how they help us in approximating functions, which is exactly the topic of the next chapter on Taylor series, so I'll see you there. When I first learned about Taylor series, I definitely didn't appreciate just how important they are. But time and time again, they come up in math and physics and many fields of engineering because they're one of the most powerful tools that math has to offer for approximating functions. I think one of the first times this clicked for me as a student was not in a calculus class, but a physics class. We were studying a certain problem that had to do with the potential energy of a pendulum. And for that, you need an expression for how high the weight of the pendulum is above its lowest point. And when you work that out, it comes out to be proportional to 1 minus the cosine of the angle between the pendulum and the vertical. Now, the specifics of the problem we were trying to solve are beyond the point here, but what I'll say is that this cosine function made the problem awkward and unwieldy, and it made it less clear how pendulums relate to other oscillating phenomena. But if you approximate cosine of theta as 1 minus theta squared over 2, of all things, everything just fell into place much more easily. Now, if you've never seen anything like this before, an approximation like that might seem completely out of left field. I mean, if you graph cosine of theta along with this function, 1 minus theta squared over 2, they do seem rather close to each other, at least for small angles near 0. But how would you even think to make this approximation? And how would you find that particular quadratic? The study of Taylor series is largely about taking non-polynomial functions and finding polynomials that approximate them near some input. And the motive here is that polynomials tend to be much easier to deal with than other functions. They're easier to compute, easier to take derivatives, easier to integrate, just all around more friendly. So let's take a look at that function, cosine of x, and really take a moment to think about how you might construct a quadratic approximation near x equals 0. That is, among all of the possible polynomials that look like c0 plus c1 times x plus c2 times x squared, for some choice of these constants, c0, c1, and c2, find the one that most resembles cosine of x near x equals 0, whose graph kind of spoons with the graph of cosine x at that point. Well, first of all, at the input 0, the value of cosine of x is 1. So if our approximation is going to be any good at all, it should also equal 1 at the input x equals 0. Plugging in 0 just results in whatever c0 is, so we can set that equal to 1. This leaves us free to choose constants c1 and c2 to make this approximation as good as we can, but nothing we do with them is going to change the fact that the polynomial equals 1 at x equals 0. Now, it would also be good if our approximation had the same tangent slope as cosine x at this point of interest. Otherwise, the approximation drifts away from the cosine graph much faster than it needs to. The derivative of cosine is negative sine, and at x equals 0, that equals 0, meaning the tangent line is perfectly flat. On the other hand, when you work out the derivative of our quadratic, you get c1 plus 2 times c2 times x. At x equals 0, this just equals whatever we choose for c1. So this constant c1 has complete control over the derivative of our approximation around x equals 0. Setting it equal to 0 ensures that our approximation also has a flat tangent line at this point. And this leaves us free to change c2. But the value and the slope of our polynomial at x equals 0 are locked in place to match that of cosine. The final thing to take advantage of is the fact that the cosine graph curves downward above x equals 0. It has a negative second derivative. Or in other words, even though the rate of change is 0 at that point, the rate of change itself is decreasing around that point. Specifically, since its derivative is negative sine of x, its second derivative is negative cosine of x, and at x equals 0, that equals negative 1. Now, in the same way that we wanted the derivative of our approximation to match that of the cosine, so that their values wouldn't drift apart needlessly quickly, making sure that their second derivatives match will ensure that they curve at the same rate, that the slope of our polynomial doesn't drift away from the slope of cosine x any more quickly than it needs to. Pulling up the same derivative we had before, and then taking its derivative, we see that the second derivative of this polynomial is exactly 2 times c2. So to make sure that this second derivative also equals negative 1 at x equals 0, 2 times c2 has to be negative 1, meaning c2 itself should be negative 1/2. And this gives us the approximation 1 plus 0x minus 1/2 x squared. And to get a feel for how good it is, if you estimate, say, cosine of 0.1 using this polynomial, you'd estimate it to be 0.995. And this is the true value of cosine of 0.1. It's a really good approximation. Take a moment to reflect on what just happened. You had 3 degrees of freedom with this quadratic approximation, the constants c0, c1, and c2. c0 was responsible for making sure that the output of the approximation matches that of cosine x at x equals 0. c1 was in charge of making sure that the derivatives match at that point. And c2 was responsible for making sure that the second derivatives match up. This ensures that the way your approximation changes as you move away from x equals 0, and the way that the rate of change itself changes, is as similar as possible to the behavior of cosine x, given the amount of control that you have. You could give yourself more control by allowing more terms in your polynomial and matching higher order derivatives. For example, let's say you added on the term c3 times x cubed for some constant c3. Well, in that case, if you take the third derivative of a cubic polynomial, anything that's quadratic or smaller goes to 0. And as for that last term, after 3 iterations of the power rule, it looks like 1 times 2 times 3 times whatever c3 is. On the other hand, the third derivative of cosine x comes out to sine of x, which equals 0 at x equals 0. So to make sure that the third derivatives match, the constant c3 should be 0. Or in other words, not only is 1 minus 1/2 x squared the best possible quadratic approximation of cosine, it's also the best possible cubic approximation. You can actually make an improvement by adding on a fourth order term, c4 times x to the fourth. The fourth derivative of cosine is actually itself, which equals 1 at x equals 0. And what's the fourth derivative of our polynomial with this new term? Well, when you keep applying the power rule over and over, with those exponents all hopping down in front, you end up with 1 times 2 times 3 times 4 times c4, which is 24 times c4. So if we want this to match the fourth derivative of cosine x, which is 1, c4 has to be 1 over 24. And indeed, the polynomial 1 minus 1/2 x squared plus 1/24 times x to the fourth, which looks like this, is a very close approximation for cosine x around x equals 0. In any physics problem involving the cosine of a small angle, for example, predictions would be almost unnoticeably different if you substituted this polynomial for cosine of x. Now take a step back and notice a few things happening with this process. First of all, factorial terms come up very naturally in this process. When you take n successive derivatives of the function x to the n, letting the power rule just keep cascading on down, what you'll be left with is 1 times 2 times 3, on and on up to whatever n is. So you don't simply set the coefficients of the polynomial equal to whatever derivative you want. You have to divide by the appropriate factorial to cancel out this effect. For example, that x to the fourth coefficient was the fourth derivative of cosine, 1, but divided by 4 factorial, 24. The second thing to notice is that adding on new terms, like this c4 times x to the fourth, doesn't mess up what the old terms should be. And that's really important. For example, the second derivative of this polynomial at x equals 0 is still equal to 2 times the second coefficient, even after you introduce higher order terms. And it's because we're plugging in x equals 0. So the second derivative of any higher order term, which all include an x, will just wash away. And the same goes for any other derivative, which is why each derivative of a polynomial at x equals 0 is controlled by one and only one of the coefficients. If instead you were approximating near an input other than 0, like maybe x equals pi, in order to get the same effect, you would have to write your polynomial in terms of powers of x minus pi, or whatever input you're looking at. This makes it look noticeably more complicated, but all we're doing is just making sure that the point pi looks and behaves like 0, so that plugging in x equals pi is going to result in a lot of nice cancellation that leaves only one constant. And finally, on a more philosophical level, notice how what we're doing here is basically taking information about higher order derivatives of a function at a single point, and then translating that into information about the value of the function near that point. You can take as many derivatives of cosine as you want. It follows this nice cyclic pattern: cosine of x, negative sine of x, negative cosine, sine, and then repeat. And the value of each one of these is easy to compute at x equals 0. It gives this cyclic pattern 1, 0, negative 1, 0, and then repeat. And knowing the values of all of those higher order derivatives is a lot of information about cosine of x, even though it only involves plugging in a single number, x equals 0. So what we're doing is leveraging that information to get an approximation around this input. And you do it by creating a polynomial whose higher order derivatives are designed to match up with those of cosine, following the same 1, 0, negative 1, 0 cyclic pattern. And to do that, you just make each coefficient of the polynomial follow that same pattern, but you have to divide each one by the appropriate factorial. Like I mentioned before, this is what cancels out the cascading effect of many power rule applications. The polynomials you get by stopping this process at any point are called Taylor polynomials for cosine of x. More generally, and hence more abstractly, If we were dealing with some other function other than cosine, you would compute its derivative, its second derivative, and so on, getting as many terms as you'd like, and you would evaluate each one of them at x equals 0. Then, for the polynomial approximation, the coefficient of each x to the n term should be the value of the nth derivative of the function, evaluated at 0, but divided by n factorial. And this whole rather abstract formula is something that you'll likely see in any text or any course that touches on Taylor polynomials. And when you see it, I want you to think to yourself that that constant term ensures that the value of the polynomial matches with the value of f. The next term ensures that the slope of the polynomial matches the slope of the function at x equals 0. The next term ensures that the rate at which the slope changes is the same at that point, and so on, depending on how many terms you want. And the more terms you choose, the closer the approximation, but the trade-off is that the polynomial you'd get would be more complicated. And to make things even more general, if you wanted to approximate near some input other than 0, which we'll call a, you would write this polynomial in terms of powers of x minus a, and you would evaluate all the derivatives of f at that input, a. This is what Taylor polynomials look like in their fullest generality. Changing the value of a changes where this approximation is hugging the original function, where its higher order derivatives will be equal to those of the original function. One of the simplest meaningful examples of this is the function e to the x around the input x equals 0. Computing the derivatives is super nice as it gets, because the derivative of e to the x is itself. So the second derivative is also e to the x, as is its third, and so on. So at the point x equals 0, all of these are equal to 1. And what that means is our polynomial approximation should look like 1 plus 1 times x plus 1 over 2 times x squared plus 1 over 3 factorial times x cubed, and so on, depending on how many terms you want. These are the Taylor polynomials for e to the x. Okay, so with that as a foundation, in the spirit of showing you just how connected all the topics of calculus are, let me turn to something kind of fun. A completely different way to understand this second-order term of the Taylor polynomials, but geometrically. It's related to the fundamental theorem of calculus, which I talked about in chapters 1 and chapters 8 if you need a quick refresher. Like we did in those videos, consider a function that gives the area under some graph between a fixed left point and a variable right point. What we're going to do here is think about how to approximate this area function, not the function for the graph itself like we've been doing before. Focusing on that area is what's going to make the second-order term kind of pop out. Remember, the fundamental theorem of calculus is that this graph itself represents the derivative of the area function. And it's because a slight nudge dx to the right bound of the area gives a new bit of area that's approximately equal to the height of the graph times dx. And that approximation is increasingly accurate for smaller and smaller choices of dx. But if you wanted to be more accurate about this change in area, given some change in x that isn't meant to approach 0, you would have to take into account this portion right here, which is approximately a triangle. Let's name the starting input a, and the nudged input above it x, so that that change is x minus a. The base of that little triangle is that change, x minus a, and its height is the slope of the graph times x minus a. Since this graph is the derivative of the area function, its slope is the second derivative of the area function, evaluated at the input a. So the area of this triangle, 1/2 base times height, is 1/2 times the second derivative of this area function, evaluated at a, multiplied by x minus a squared. And this is exactly what you would see with a Taylor polynomial. If you knew the various derivative information about this area function at the point a, how would you approximate the area at the point x? Well, you have to include all that area up to a, f of a, plus the area of this rectangle here, which is the first derivative times x minus a, plus the area of that little triangle, which is 1/2 times the second derivative times x minus a squared. I really like this, because even though it looks a bit messy all written out, each one of the terms has a very clear meaning that you can just point to on the diagram. If you wanted, we could call it an end here, and you would have a phenomenally useful tool for approximations with these Taylor polynomials. But if you're thinking like a mathematician, one question you might ask is whether or not it makes sense to never stop and just add infinitely many terms. In math, an infinite sum is called a series. So even though one of these approximations with finitely many terms is called a Taylor polynomial, adding all infinitely many terms gives what's called a Taylor series. You have to be really careful with the idea of an infinite series, because it doesn't actually make sense to add infinitely many things. You can only hit the plus button on the calculator so many times. But if you have a series where adding more and more of the terms, which makes sense at each step, gets you increasingly close to some specific value, what you say is that the series converges to that value. Or, if you're comfortable extending the definition of equality to include this kind of series convergence, you'd say that the series as a whole, this infinite sum, equals the value that it's converging to. For example, look at the Taylor polynomial for e to the x, and plug in some input, like x equals 1. As you add more and more polynomial terms, the total sum gets closer and closer to the value e. So you say that this infinite series converges to the number e, or what's saying the same thing, that it equals the number e. In fact, it turns out that if you plug in any other value of x, like x equals 2, and look at the value of the higher and higher order Taylor polynomials at this value, they will converge towards e to the x, which in this case is e squared. And this is true for any input, no matter how far away from 0 it is, even though these Taylor polynomials are constructed only from derivative information gathered at the input 0. In a case like this, we say that e to the x equals its own Taylor series at all inputs x, which is kind of a magical thing to have happen. And even though this is also true for a couple other important functions, things like sine and cosine, sometimes these series only converge within a certain range around the input whose derivative information you're using. If you work out the Taylor series for the natural log of x around the input x equals 1, which is built by evaluating the higher order derivatives of the natural log of x at x equals 1, this is what it would look like. When you plug in an input between 0 and 2, adding more and more terms of this series will indeed get you closer and closer to the natural log of that input. But outside of that range, even by just a little bit, the series fails to approach anything. As you add on more and more terms, the sum just kind of bounces up back and forth wildly. It does not, as you might expect, approach the natural log of that value, even though the natural log of x is perfectly well defined for inputs that are above 2. In some sense, the derivative information of ln of x at x equals 1 doesn't propagate out that far. In a case like this, where adding more terms of the series doesn't approach anything, you say that the series diverges. And that maximum distance between the input you're approximating near and points where the outputs of these polynomials actually do converge is called the radius of convergence for the Taylor series. There remains more to learn about Taylor series. There are many use cases, tactics for placing bounds on the error of these approximations, tests for understanding when series do and don't converge. And for that matter, there remains more to learn about calculus as a whole, and the countless topics not touched by this series. The goal with these videos is to give you the fundamental intuitions that make you feel confident and efficient in learning more on your own, and potentially even rediscovering more of the topic for yourself. In the case of Taylor series, the fundamental intuition to keep in mind as you explore more of what there is that they translate derivative information at a single point to approximation information around that point. Picture yourself as an early calculus student about to begin your first course. The months ahead of you hold within them a lot of hard work, some neat examples, some not so neat examples, beautiful connections to physics, not so beautiful piles of formulas to memorize, plenty of moments of getting stuck and banging your head into a wall, a few nice aha moments sprinkled in as well, and some genuinely lovely graphical intuition to help guide you through it all. But if the course ahead of you is anything like my first introduction to calculus, or any of the first courses that I've seen in the years since, there's one topic that you will not see, but which I believe stands to greatly accelerate your learning. You see, almost all of the visual intuitions from that first year are based on graphs. The derivative is the slope of a graph, the integral is a certain area under that graph. But as you generalize calculus beyond functions whose inputs and outputs are simply numbers, it's not always possible to graph the function that you're analyzing. There's all sorts of different ways that you'd be visualizing these things. So if all your intuitions for the fundamental ideas, like derivatives, are rooted too rigidly in graphs, it can make for a very tall and largely unnecessary conceptual hurdle between you and the more quote-unquote advanced topics like multivariable calculus and complex analysis, differential geometry. Now what I want to share with you is a way to think about derivatives, which I'll refer to as the transformational view, that generalizes more seamlessly into some of those more general contexts where calculus comes up. And then we'll use this alternate view to analyze a certain fun puzzle about repeated fractions. But first off, I just want to make sure that we're all on the same page about what the standard visual is. If you were to graph a function, which simply takes real numbers as inputs and outputs, one of the first things you learn in a calculus course is that the derivative gives you the slope of this graph. Where what we mean by that is that the derivative of the function is a new function, which for every input x returns that slope. Now I'd encourage you not to think of this derivative as slope idea as being the definition of a derivative. Instead, think of it as being more fundamentally about how sensitive the function is to tiny little nudges around the input. And the slope is just one way to think about that sensitivity, relevant only to this particular way of viewing functions. I have not just another video, but a full series on this topic if it's something you want to learn more about. Now the basic idea behind the alternate visual for the derivative is to think of this function as mapping all of the input points on the number line to their corresponding outputs on a different number line. In this context, what the derivative gives you is a measure of how much the input space gets stretched or squished in various regions. That is, if you were to zoom in around a specific input and take a look at some evenly spaced points around it, the derivative of the function of that input is going to tell you how spread out or contracted those points become after the mapping. Here, a specific example helps. Take the function x squared. It maps 1 to 1, and 2 to 4, 3 to 9, and so on. And you could also see how it acts on all of the points in between. And if you were to zoom in on a little cluster of points around the input 1, and then see where they land around the relevant output, which for this function also happens to be 1, you'd notice that they tend to get stretched out. In fact, it roughly looks like stretching out by a factor of 2. And the closer you zoom in, the more this local behavior looks just like multiplying by a factor of 2. This is what it means for the derivative of x squared at the input x equals 1 to be 2. It's what that fact looks like in the context of transformations. If you looked at a neighborhood of points around the input 3, they would get roughly stretched out by a factor of 6. This is what it means for the derivative of this function at the input 3 to equal 6. Around the input 1/4, a small region actually tends to get contracted, specifically by a factor of 1/2. And that's what it looks like for a derivative to be smaller than 1. Now the input 0 is interesting. Zooming in by a factor of 10, it doesn't really look like a constant stretching or squishing. For one thing, all of the outputs end up on the right positive side of things. And as you zoom in closer and closer by 100x or by 1000x, it looks more and more like a small neighborhood of points around 0 just gets collapsed into 0 itself. And this is what it looks like for the derivative to be 0. The local behavior looks more and more like multiplying the whole number line by 0. It doesn't have to completely collapse everything to a point at a particular zoom level. Instead, it's a matter of what the limiting behavior is as you zoom in closer and closer. It's also instructive to take a look at the negative inputs here. Things start to feel a little cramped since they collide with where all the positive input values go. and this is one of the downsides of thinking of functions as transformations. But for derivatives, we only really care about the local behavior anyway. What happens in a small range around a given input. Here, notice that the inputs in a little neighborhood around, say, -2, they don't just get stretched out, they also get flipped around. Specifically, the action on such a neighborhood looks more and more like multiplying by -4 the closer you zoom in. This is what it looks like for the derivative of a function to be negative. And I think you get the point, this is all well and good, but let's see how this is actually useful in solving a problem. A friend of mine recently asked me a pretty fun question about the infinite fraction 1 plus 1 divided by 1 plus 1 divided by 1 plus 1 divided by 1, on and on and on and on. And clearly you watch math videos online, so maybe you've seen this before, but my friend's question actually cuts to something that you might not have thought about before, relevant to the view of derivatives that we're looking at here. The typical way that you might evaluate an expression like this is to set it equal to x, and then notice that there's a copy of the full fraction inside itself. So you can replace that copy with another x, and then just solve for x. That is, what you want is to find a fixed point of the function 1 plus 1 divided by x. But here's the thing, there are actually two solutions for x, two special numbers, where 1 plus 1 divided by that number gives you back the same thing. One is the golden ratio, phi, around 1.618, and the other is -0.618, which happens to be -1 divided by phi. I like to call this other number phi's little brother, since just about any property that phi has, this number also has. And this raises the question, would it be valid to say that that infinite fraction that we saw is somehow also equal to phi's little brother, -0.618? Maybe you initially say, obviously not. Everything on the left-hand side is positive, so how could it possibly equal a negative number? Well, first we should be clear about what we actually mean by an expression like this. One way that you could think about it, and it's not the only way, there's freedom for choice here, is to imagine starting with some constant, like 1, and then repeatedly applying the function 1 plus 1 divided by x. And then asking, what is this approach as you keep going? I mean, certainly symbolically, what you get looks more and more like our infinite fraction, so maybe if you want it to equal a number, you should ask what this series of numbers approaches. And if that's your view of things, maybe you start off with a negative number, so it's not so crazy for the whole expression to end up negative. After all, if you start with -1 divided by phi, then applying this function, 1 plus 1 over x, you get back the same number, -1 divided by phi. So no matter how many times you apply it, you're staying fixed at this value. But even then, there is one reason that you should probably view phi as the favorite brother in this pair. Here, try this. Pull up a calculator of some kind, then start with any random number, and then plug it into this function, 1 plus 1 divided by x, and then plug that number into 1 plus 1 over x, and then again, and again, and again, and again, and again. No matter what constant you start with, you eventually end up at 1.618. Even if you start with a negative number, even one that's really, really close to phi's little brother, eventually it shies away from that value and jumps back over to phi. So what's going on here? Why is one of these fixed points favored above the other one? Maybe you can already see how the transformational understanding of derivatives is going to be helpful for understanding this setup. But for the sake of having a point of contrast, I want to show you how a problem like this is often taught using graphs. If you were to plug in some random input to this function, the y value tells you the corresponding output, right? So to think about plugging that output back into the function, you might first move horizontally until you hit the line y equals x, and that's going to give you a position where the x value corresponds to your previous y value, right? So then from there, you can move vertically to see what output this new x value has. And then you repeat. You move horizontally to the line y equals x to find a point whose x value is the same as the output that you just got, and then you move vertically to apply the function again. Now, personally, I think this is kind of an awkward way to think about repeatedly applying a function, don't you? I mean, it makes sense, but you kind of have to pause and think about it to remember which way to draw the lines. And you can, if you want, think through what conditions make this spiderweb process narrow in on a fixed point versus propagating away from it. And in fact, go ahead, pause right now and try to think it through as an exercise. It has to do with slopes. Or, if you want to skip the exercise for something that I think gives a much more satisfying understanding, think about how this function acts as a transformation. So I'm going to go ahead and start here by drawing a whole bunch of arrows to indicate where the various sampled input points will go. And side note, don't you think this gives a really neat emergent pattern? I wasn't expecting this, but it was cool to see it pop up when animating. I guess the action of 1 divided by x gives this nice emergent circle, and then we're just shifting things over by 1. Anyway, I want you to think about what it means to repeatedly apply some function, like 1 plus 1 over x, in this context. Well, after letting it map all of the inputs to the outputs, you could consider those as the new inputs, and then just apply the same process again, and then again, and do it however many times you want. Notice, in animating this with a few dots representing the sample points, it doesn't take many iterations at all before all of those dots kind of clump in around 1.618. Now remember, we know that 1.618 and its little brother, negative 0.618 on and on, stay fixed in place during each iteration of this process. But zoom in on a neighborhood around phi. During the map, points in that region get contracted around phi, meaning that the function, 1 plus 1 over x, has a derivative with a magnitude that's less than 1 at this input. In fact, this derivative works out to be around negative 0.38. So what that means is that each repeated application scrunches the neighborhood around this number smaller and smaller, like a gravitational pull towards phi. So now tell me what you think happens in the neighborhood of phi's little brother. Over there, the derivative actually has a magnitude larger than 1, so points near the fixed point are repelled away from it. And when you work it out, you can see that they get stretched by more than a factor of 2 in each iteration. They also get flipped around because the derivative is negative here, but the salient fact for the sake of stability is just the magnitude. Mathematicians would call this right value a stable fixed point, and the left one is an unstable fixed point. Something is considered stable if when you perturb it just a little bit, it tends to come back towards where it started, rather than going away from it. So what we're seeing is a very useful little fact, that the stability of a fixed point is determined by whether or not the magnitude of its derivative is bigger or smaller than 1. And this explains why phi always shows up in the numerical play where you're just hitting enter on your calculator over and over, but phi's little brother never does. Now, as to whether or not you want to consider phi's little brother a valid value of the infinite fraction, well, that's really up to you. Everything we just showed suggests that if you think of this expression as representing a limiting process, then because every possible seed value other than phi's little brother gives you a series converging to phi, it does feel kind of silly to put them on equal footing with each other. But maybe you don't think of it as a limit. Maybe the kind of math you're doing lends itself to treating this as a purely algebraic object, like the solutions of a polynomial, which simply has multiple values. Anyway, that's beside the point. And my point here is not that viewing derivatives as this change in density is somehow better than the graphical intuition on the whole. In fact, picturing an entire function this way can be kind of clunky and impractical as compared to graphs. My point is that it deserves more of a mention in most of the introductory calculus courses, because it can help make a student's understanding of the derivative a little bit more flexible. But like I mentioned, the real reason that I'd recommend you carry this perspective with you as you learn new topics is not so much for what it does with your understanding of single variable calculus, it's for what comes after.